Hi everyone, welcome to the stream. Sorry about the delay. There was a package I was waiting to be delivered. So now we're finally ready to start. So let me just check if the stream is okay. Okay, so it is live. Okay, great. Hi. Let me just, yeah. So today we're going to talk about integral transforms, and in particular, Laplace and Fourier transform. So I'm actually going to prioritize Fourier transform. Hi, Steve. Thank you very much for joining the stream. I'm sorry for letting you guys wait. So today we're going to talk about integral transforms, Fourier transform, Laplace transform, and also to some degree Z transform. Of course, these aren't the only transforms. Okay, so integral transform is a big subject, is a big field, and it's very beautiful. It's also very useful. It's also it's just very useful in both pure and applied mathematics. Here, I mean, we're doing mostly applied mathematics, but we will emphasize what role do transforms play when it comes to pure mathematics as well, because this is certainly one of the crown jewels of both classical and modern mathematics. So actually, we're going to slightly biased, I mean, perhaps not so slightly, but heavily biased towards Fourier analysis, Fourier transform. So the reason for that is because we are getting into PDEs. Right now, we're still in the first order PDE, first order nonlinear PDEs, but the focus of our PDE sessions and episodes is going to be introductory, and it's going to be mostly linear PDEs, and Fourier transform method will play a big part. And for example, we already seen the heat equation in both our videos and live stream. So for example, in this week earlier, in our first episode for stochastic processes for a physicist, we already seen the heat equation, right? So and we made the conclusion that the solution to the heat equation is a Gaussian, right? A Gaussian. So how do you obtain that result? And it's actually through Fourier transform. Perhaps the most popular method to get that is to use Fourier transform. And of course, Fourier transform can be used to solve all sorts of linear PDEs. So what about Legendre transform? So Legendre transform is a little bit different. I mean, I assume you're talking about the Legendre transform for convex function, right? So so the Legendre transform is a little bit different. So it's not an integral transform, although I think you can. There is a Legendre transform that is also an integral transform. So there is going to be a little bit of a ambiguity there. But today we're not going to talk about Legendre transform. Perhaps we will talk about Legendre transform in one of our calculus of variation sessions. So yeah, it is also a transform in the sense that it preserves information exactly. Hi Vernon. So it's to be a transform, you have to be the transform needs to be one-to-one, and the idea is you don't lose information. You can transform a function to a new function and get it back. Right? That's the idea. Are you doing wavelet transform? Not today, but we will talk about wavelets. Okay, we'll talk about wavelet, and it's the wavelet transform is a natural next step for Fourier transform. But today we're going to stick to the classic stuff, mostly aimed at the PDEs. Okay, of course, things are, you don't necessarily need to solve a PDE. Right? For example, Fourier transform is used in signal analysis. Right? So anyway, this is a brief list of resources that I compiled. Okay. In the description. So you can go to the description and see some of the links I've written. Okay, I've given. So here this is an overarching message actually. This is my understanding, okay? So I guess right now the Fourier analysis, harmonic analysis, is now a very abstract and highly advanced subject, okay? Perhaps this is already a kind of a limited understanding, but it works in a lot of applied scenarios. Yeah, no worries. I enjoy doing what I do. So here you see we have this idea. Okay, we'll explain that in a bit. The overarching idea of all kinds of integral transform is to linearly map a function in a one-to-one manner into another vector space and then represent the image with respect to some convenient basis, typically eigenbasis. Okay, so we will see what this means. So to understand integral transforms, yes, intuitively, you really just need linear algebra to get it. Of course, for more sophisticated transforms, proving one-to-oneness becomes more difficult. And interpretation of so-called one-to-oneness also becomes more difficult. This is where other subjects such as complex analysis and measure theory comes into play. But really, to understand the fundamental intuition, you just need a linear algebra. Okay, and here I've listed three transforms, perhaps the most highly used ones in applied mathematics: Z transform, Laplace, and Fourier. So in a nutshell, Z transform is used for sequences. Okay, for sequences, that is discrete functions, basically. Functions that is discrete time signal. Okay, and Laplace transform is used for function defined on the positive axis, whereas Fourier transform is used for functions defined on the entire real axis. Okay, so these are the most commonly used transform, but the integral transforms is a large domain, which include other members. So for Z transforms, you typically don't see a dedicated single source of textbook, for example, on Z transform alone. It is usually incorporated in signal analysis textbook as a separate chapter. Will you save the stream? Yes, of course. All my streams are on the live tab. You can go check it out. This is an introductory textbook for electrical engineering called Linear Systems and Signals. This is very comprehensive and very approachable by Lathi and Green. There is a separate chapter, chapter 5, on Z transform. Okay, so there's that. And we also have integral transforms for a textbook for integral transform. So two of which I really like are Operational Mathematics by Churchill. So if you are in applied mathematics, you probably know there's a textbook by Brown and Churchill on complex variables, as well as Fourier series. And this one, unfortunately, is currently out of print, but the quality is still superb. Even though it is kind of old, but the quality is still superb. The mathematics has not aged a single day. Unfortunately, currently it's out of print. So try to get a copy or electronic version if you can. But this is a great resource. And a graduate level text is as follows. Oh, by the way, I just want to mention the prerequisite for reading Churchill is just regular calculus, just the standard sequence of calculus. Some background in ordinary differential equation is desirable. However, it's not necessary because most of the book actually develops the method for solving differential equations. Okay, you just need to know what a differential equation is, pretty much, and how to model with differential equations. The solution methods aren't typically very important because this book is all about developing solution methods using integral transform. So back in the days, integral transforms is called operational mathematics, developed by Oliver Heaviside. You guys know this person, Oliver Heaviside. He was a British mathematician, a maverick, very anti-establishment, as a physicist who quote unquote, literally transformed the field of electrical engineering. So nowadays we owe many aspects of modern civilization to him. So yeah, he formulated the telegrapher's equation, became commercially important, as well as using complex numbers to represent alternate current. It's an excellent application of complex numbers. We'll mention that as well, because fundamentally it's all tied to integral transforms, actually. So Oliver Heaviside, so he proposed a new technique for solving differential equations known as operational calculus, operational mathematics. But at the time it was viewed with great suspicion. And then mathematicians tried to justify his method using the theory of Laplace transform. So nowadays, the operational mathematics, the term operational mathematics is rarely used. However, the content is largely the same as integral transform. All right, so I was talking about this introductory undergraduate level book, excellent quality. Here, and a graduate level text, this one, oh, by the way, operational mathematics do not assume complex analysis. Just want to make sure. Okay, this one does not assume complex analysis. The next one does. This one is a graduate level text, and it goes beyond Laplace and Fourier. This one is much more comprehensive. It's called Integral Transforms in Application by Lokenath Debnath and others. So yeah, check out this one if you want a more encyclopedic treatment. Okay, and here we have a few courses on transforms. Two of them are from Stanford. One of which, in particular, this one is highly recommended, EE 261. So if you go to the course website, is it here? Yeah, it's here. How about the book by Stein? Stein is more rigorous, for sure. Yeah, Stein's Fourier analysis is more rigorous. So here because this stream is not particularly mathematically rigorous, we're going to provide a motivation of why this is useful. Stein's analysis series is excellent. Okay, but I think probably it's better for pure math majors. Okay, and if you want to know the details, so for example, the convergence of Fourier series, that's an excellent source. Stein's analysis is great. Hi Andre, thank you for joining the stream. Hi Christian, thank you for joining the stream. So yeah, Ken was talking about Fourier analysis by Stein. So that's a proper harmonic analysis textbook. Okay, and it is highly regarded. So go ahead and check out this one. Introduction to Fourier. Stein is actually a harmonic analyst. See, this is a very highly cited textbook. Excellent. That being said, Stein's style is rather terse, in my opinion. Is rather dense, and his exercises are hard. So I don't recommend this for complete beginners or for applied scientists. Not as a first introduction. Okay, but this is great for mathematicians. Okay, so now come back to these two resources from Stanford. This one, called EE 261, it's got full lectures, recording, handouts, and assignments, also textbook. Okay, textbook is not for free. Okay, textbook, the textbook written by Professor Osgood, the instructor, is a separate textbook. Okay, so he has written a textbook, Fourier transform and its application. This is electrical engineering, because this is EE. This is electrical engineering, so it is great for applied scientists. You see, we talk about things like the direct delta function, convolution and correlation applications, probability distribution, sampling theory, filters, analysis of linear systems, discrete Fourier transform and fast Fourier transform, things like that. Okay, so for example, I don't think Stein's analysis covers fast Fourier transform. If you're an applied scientist, this is perhaps one of the most important algorithms you will ever see. Okay, so that's why this particular live session isn't focused on mathematical rigor. It's more about intuition and why this is such a powerhouse, okay, in applied mathematics. It's kind of unbelievable because I've been running this channel for 2 years and I only published 2 videos on Fourier stuff, and both are like integral calculation essentially. It's not really particularly intuitive. I mean, it's a specific result in Fourier analysis. Basically, if you go to the channel, I publish 2 videos on how do you calculate Fourier transform using contour integration. Okay, but anyway, that's not super important right now. Okay, and another course also offered by Stanford is this one. Is Math 264. Actually, 262. I don't think this one is now continued. So this is an old course, but it's gold. It covers the later chapter combined with group. Exactly, right? That's the modern perspective. Right? That's actually the modern harmonic analysis is done on locally compact abelian groups, right? Which is perhaps already the standard of, this is already the standard setup in modern harmonic analysis, but still, like, it's still not the dominant technique. Still, it takes time for it to seep into applied sciences. It's great. It's great on its for its own sake, but we're not at that level yet. All right, so we're talking about this one, Math 262, called Applied Fourier Analysis and Elements of Modern Signal Processing. And here, this is an MRI image, because MRI image is a Fourier transform. Okay, so these are the syllabus. The syllabus, perhaps most importantly, let's take a look at the handouts. You can see what's being emphasized here. Okay, just some highlight. X-ray tomography, magnetic resonance imaging, wave optics. So this is very applied. I think this will be highly interesting for applied scientists and engineers. So go check this one out. Okay. Also, there's a previous edition. Oh, what's going on? Okay, that's a course package. Anyway, doesn't matter. So basically, yeah, these two are highly recommended to applied scientists interested in getting into transform method. And Chad already mentioned Wavelets. And this is a course from University of Waterloo called AMAS 391, From Fourier to Wavelet, by Professor Edward Versky. So these are the lecture notes. So I think for the first half or so, it's all Fourier stuff. It's geared towards signal analysis. Yeah, starting from, yeah, this actually earlier, week 7. It started to talk, yeah, I think week 7 it then started to talk about the wavelet stuff. Okay, so convolution theorem, the Fourier analysis, all kinds of filter. So this is like signal processing, but for mathematicians. Okay, it's slightly more rigorous, but it does not assume anything like measure theory. The idea of functional analysis are introduced along the way, but still the main objective is geared towards applications, in particular image and signal analysis, signal processing. Okay, so there's that. Where's the, yeah, so wavelet transform wavelet analysis is a direct not analogy, generalization of Fourier stuff. Sampling theorem, I think wavelet is okay. So basically, over half of the course of AMATS 391 is about Fourier stuff. Like about 2/3 of the course. Hold on, what's going on? 2/3 of the course is about Fourier stuff, and the rest of the 1/3 is wavelet. Okay, so also very accessible. Professor Verske's notes are very conversational, very chatty and approachable. It's a shame that we don't have much exercises on the website, but if you guys are interested in exercises, I can find extra resources too. And actually, I figured a way to compile book recommendation or resource recommendation list, actually, because I have been having this problem on my Discord server, because often people request resources, resource recommendations, things like that. And every time I have to answer it, right? I have to answer it. Okay, so for example, the most common question I get is, what statistics book you recommend? Okay, what probability book you recommend? Every time I have to answer the same thing. So it's not the most convenient for me. I figured, why don't we just make use of the YouTube comment section as well as description? You know, I'll just put my recommendation in the video and stream description. So the thing is, if I would just put, like, let's say, later on I will add a extra text in the title and say, the joy of integral transforms with resource recommendations, with book recommendations. And so this way, if you go to my channel and you just search book recommendation, you immediately will find that stream or that video, and you'll see it in the description, and people can contribute in the chat, or in the comments. Right? So now we're doing live chat, right? So after the stream is finished, we'll get comment sections, and I will compile notable examples in chat, in a pinned comment, and other people who watch the stream recording can also provide their own recommendation. So we can have the discussion going. And this way, I don't always have to answer the same question over and over, because sometimes it's difficult for me to, for example, remember, okay, what's the course number from Stanford, right? I think that will be a method that solves the book recommendation list. Because initially I thought maybe I should do a Google Drive, but that's not the most convenient, right? Most people just hear for the YouTube stuff. Discord is already a bit of a, asking people to join the Discord is already extra effort, right? So why don't we just do it in the features already provided by YouTube, okay? So it's unlikely I will be making dedicated book review videos because I simply no longer enjoy making them. But still, whenever we start a new subject, this question is unavoidable. Right? So I will just do it in a single stream, a single, say, for example, a single video, not perhaps, as I said, not video, just single stream, the one that started the series, and then you will see it right, in the description, in the comment section. Because typically I don't recommend things that I've never had any experience with. For example, let's say if you ask me, what do you recommend for number theory? I just literally have no recommendation whatsoever, because we don't do number theory on the channel. Well, at least not number theory in any substantial form, right? Like, I mean, maybe we can prove the fundamental theorem of arithmetic, but that's pretty much going to be it, okay? Because that's simply beyond my expertise, and I don't want to recommend things. I don't want to just Google, say, what's the most popular number theory book, and it'll provide you that answer. That's not my experience. That's not my opinion. So it's kind of pointless for me to give you that information, right? So whatever we do on the channel, right, we do on the channel, we'll have a book recommendation, resource recommendation list. And I just came up with this idea today. I recommended the natural numbers for number theory. Yeah, exactly. So, like, by all means, like, the viewers can suggest such resources among themselves, but I won't do that. Okay. If I have limited experience about a subject, I'll just tell you I have limited experience. Right? If I have no experience, I'll just tell you I have no experience. I have nothing to recommend. I'm sorry, but that's pretty much going to be it. Okay, so that's enough about resource recommendations for this field. This is really beautiful. This is such a beautiful field. And I just want to mention that even though sometimes things aren't called transforms, they're essentially the same thing. Because the idea of transform is so far-reaching in math as a whole that sometimes we're using the same idea without calling it. For example, Z-transform is also used in combinatorics, called a generating function. And this is a canonical text for generating function in discrete mathematics, in particular combinatorics, called generatingfunctionology. Generatingfunctionology. Okay, it's a made-up word, but it's a funny one. So yeah, it's a freely downloadable, and it's a pretty comprehensive text when it comes to using transform methods to solve counting problems. It's highly interesting. Okay, so perhaps we'll do some discrete mathematics someday. It's the same idea as Z-transform, really. Okay, and in probability theory, the transform method is also everywhere. The Z-transform is called the probability generating function. We already seen one in our PDE stream. In our first introduction to PDE, we give an example. That is the stochastic process called the burst and death process. The burst and death process satisfies a complicated differential equation, which is the Kolmogorov-Forward equation, also known as Master's equation. Actually, we'll get to Master's equation next week. Okay, and solving it directly is very, very difficult. So what do? We use a Z-transform and get the probability generating function. And it turns out that the probability generating function satisfies a PDE, which is first order linear PDE, and then can be solved using standard techniques in PDE. So it's really an ingenious technique. So in probability series, Z-transform is called probability generating function. It's for integer value random variables. The Laplace transform in probability theory is essentially the same as the moment generating function called MGF. So MGF, if you've taken an introductory probability textbook, if you've taken an introductory probability course, you've probably seen the MGF. It's essentially the same as Laplace transform. It feels rather unmotivated in treatment of probability, but as we shall see, there's no mystery to it. It's just a Laplace transform, which in turn is what? Is a linear map of a function in a one-to-one manner into another vector space, and then represent the image with respect to some convenient basis. And the Fourier transform in probability theory is called a characteristic function. And typically, undergraduate level, you only see a moment generating function, whereas at graduate level probability, the characteristic function is used pretty much all the time in place of moment generating function. Now, the Fourier transform is the preferred transform in probability theory. And yeah, so even though things aren't called transform, they're just the same idea. So this is a extremely fruitful, wide-reaching tool. Okay, and on the pure mathematics side, the desire to understand Fourier transform pretty much built the foundation of modern real analysis. Measure theory came out of Fourier transform, came out of the attempt to understanding Fourier transform and Fourier series. And heck, the definition of real numbers came out of the need to understand Fourier series. So yeah, the definition of a real number was unsolved for at least 2,000 years. And mathematicians was just kind of sweeping it under the rug. They knew there was something mysterious going on with the real numbers, but when it comes to understanding Fourier series, they could no longer do so. So that's why in the mid and late part of the 19th century, the foundations of real analysis, the foundation of calculus, underwent a complete scrutiny. So these tools, they came out of practical needs, but they shaped modern pure mathematics. All right, so that's enough about this overview, resource recommendation. I know it's perhaps a little bit overwhelming, but I just wanted to give shout out to the resources that I benefited from. Okay. I got a lot of mileage from Mellin transform in my research. Yes, Mellin transform, for example, is covered in this one, integral transform and applications. These are more exotic transforms, but they are powerful in particular domains. Okay, so let's just take a look at I'm just going to start with the notes here. So what do we mean by a transform? So let's start with the most basic example of Z transform. Okay, so consider a sequence. It's a sequence of real numbers. Let's just call it AN. All right. So it's an infinite list. So it's A0, A1, A2, and so on. Okay, n greater or equal to 0. So this is a sequence of real numbers. Okay, so what is a sequence of real numbers formally? It is a function. The sequence of real numbers is a function. This is a function that maps from the set of natural numbers, including 0, to real. So this is a function. A sequence of real numbers is a function. So this is an idea due to Euler. The sequence of real numbers is a discrete object, but it has a one-to-one correspondence with a continuous object. What's that? Well, the sequence AN has a one-to-one correspondence with a power series, the sum of AN x to the n, where n goes from 0 to infinity. How much till we get to the limitation advantage of real versus discrete transform? What do you mean by limitation advantage of real discrete transform? You will see along the way, I guess. I'm not quite sure about the, perhaps answering the question of like the limitations of Fourier transform, we will have to do a complete survey, which will take us weeks at least. Okay. Indeed, the disadvantage or the limitations of Fourier transform is what motivated wavelets. Okay. That's one way to put it. Okay. But so far we're trying to look at why is a tool valuable rather than looking at, okay, where does it fail? Okay. Different stages of question, I suppose. Okay, I apologize if that answer is somewhat disappointing. Now, this is an idea due to Euler. Actually, because it's called a Z transform, we're going to use a variable Z. Right? That's the dominant variable, the traditional variable for the power series. This is a power series. So this is a sequence. It has a one-to-one correspondence with a power series. If you know the sequence, you can build a power series. And we're not going to discuss the convergence of the power series. Okay, this is a so-called formal power series. formal power series. You know, I always find it funny that the word formal in mathematics has opposite meaning. Sometimes we say, oh, the derivation is purely formal. It means that we don't care about convergence. Okay, you don't care about whether each step is justifiable. Okay, just the formal, just to provide some intuition. And this is a formal derivation. It's not rigorous. But then we say a formal proof, which means completely rigorous. So it drives non-mathematicians crazy. But here, a formal power series means a power series without considering whether this actually converges to a complex number. Typically, Z is a complex number. So this is called a formal power series. Let's just take a look at an example. Hi Sha, thanks for joining the stream. So if you have a constant series, just an equals to a constant 1, right? The corresponding series is what? An z to the n is just the sum of z to the n. And this is, of course, the familiar geometric series. It's just 1 over 1 minus z. Okay? So there you have the power series, which is a function in z. How do you recover the coefficient? Well, of course, you can say, oh, I just use the geometric series. But if you don't know the geometric series formula, you can use the Taylor formula, a Taylor expansion formula. Right? So if this is a function called f of z, to get the coefficients an, you can take the derivative of f. An is f's nth order derivative evaluated at 0 over n factorial. N equals 0, 1, 2, and so on. So this is really the idea of a transform. It's a duality. You can transform a discrete object into a continuous object from a sequence to a power series without losing any information. So that's the idea. But isn't this a little bit arbitrary? Isn't this, why do we pick power series, for example? Why is this helpful? Why is this helpful? Perhaps we can see two concrete examples. Why is it helpful? Why this is taking a sequence into a series is helpful? Why is it helpful? Let's take a look at two examples. Example number 1, let's consider probability theory. So let x and y be two random variables that are non-negative integer valued. So example 1 is from probability. Say let x and y be discrete random variables which takes values in a range of 0, 1, 2, and so on. Okay, to describe their distribution, of course, we use the probability mass function, the PMS. The PMS for x is the probability of big X equals, say, n, and this is denoted as, just say an. Okay, let's just call it an. Of course, this is a sequence, and the probability of y equals m is another sequence. Let's just call it bm. Okay, so a natural question is, what is the distribution of the sum of x plus y? The distribution, oh actually, let me also assume that these two are independent. Be independent discrete random variables. Okay, assume independence. This is an extremely common problem in probability. The distribution of x plus y. Okay? Well, namely what we want is a formula for the probability of x plus y equals k. We want that, and let's call it ck, where k goes from, of course, k can be 0, 1, 2, and so on. It's also integer valued, non-negative integer valued. I feel like formal means symbolic. Exactly. So formal it's one of the meaning of formal. In mathematical literature, the word formal is ambiguous as hell. Sometimes it means non-rigorous, sometimes it means extremely rigorous. It really depends on the context. So yeah, mathematicians are weird. Yeah, so for example, you can consider much of the manipulation with direct delta function. F of x minus x, f of x minus y. I think that's the definition, delta y. Or actually, you know what? I don't know what I'm talking about. Let me, the delta function, I don't know, today we have time to get to the delta function, but I made a video about the Green's function, including the delta. Yeah, so this is the formula. So much of the manipulation with direct delta function in physics, by mathematical standard, is not rigorous. It's purely formal. It's purely formal. It's not. There's no rigorous meaning assigned to these symbols. Is what it means. Okay. Sometimes it's done by analogy with the discrete case. Actually, we will do that too. But sometimes the word formal can mean formal proof, which means extremely rigorous. Everything is defined in terms of set theory and things like that. For example, our ongoing series of stochastic calculus is informal in that sense because I have not defined stochastic process in terms of filtration, sigma algebra, the kind of stuff. So that's informal. And this is kind of just, yeah, formal logic means symbolic logic is the most rigorous form of logic so far, where formal power is really just an algebraic way of manipulating coefficient. Exactly. So this formal means we don't care about convergence. This, to be precise, that's basically means we don't care about convergence. We just care about how the coefficients are manipulated. Exactly. So anyway, enough of that. Mass culture, I guess. Yeah. So anyway, let's come back to deriving this ck. How do you derive the ck? Well, there's an easy way to do so, and a visual way to do so. This is the solution. So why don't we represent the joint distribution as a table? So joint distribution of x and y can be represented as a table. So this is the row for the value of x, and column values are for, let me just write it this way. Okay, this is x, this is y. X can be 0, 1, 2, 3, and so on. And y can be 0, 1, 2, 3, 4, and so on. Okay, and each entry, the entry stands for the probability of big X equals little n, and which means joint event, and y equals little m as well. All right. Because of independence assumption, this is just the product of x equals n times the probability of y equals m. Right, so there we go. We have these entries. So the 0, 0 entry is just a0 times b0. Remember, an is the probability of xn equals n. Let me just write it that way. This is just an times bm. Okay, so I can fill out these entries. a0, b0, a0, b1, a0, b2, a0, b3. It's going to take me a while to write these, but yeah. A1, B0, A1, B1, A1, B2, A1, B3, A1, B4. You get the idea. A2, B1, A2, B0, A2. Oh, joy division. Somebody recognized the reference, huh? Excellent. Excellent. Yes, the cover was the original signal by the first discovered pulsar called CP1919. Okay, I mean, I'll show you guys the image in a bit. But yeah, it was later taken as an album cover by a famous post-punk band called Joy Division, which is now currently, the image is now currently one of the most iconic image in music history. A3, B0, A3, B1, A3, B2, A3, B3, A3, B4, A4, B0, A4, B1, A4, B2, A4, B3, and A4, B4. Right? And of course, the pattern goes on forever, like this goes on. This is an infinite table. Heard the album back in the early 80s. Yeah. It's a shame that they only have 2 albums. Insider knows what happened, right? It's a famous story, but tragic, but still kind of bittersweet, I guess. Anyway, so where do we get the distribution of C from this table? Well, if we fix K, which means we're treating the sum of x and y equals constant. In the diagram, in the table, these are just the diagonals in going this way. So for example, here, the left upper corner, C is just 0, because both x and y are 0. There's only one possibility, basically. If C equals 0, x and y must both be 0. If, say, C is 1, K is 1, not C is 1. Okay, x plus y is 1. That means you have 2 possibilities. X can be x equals 0, y equals 1, or x equals 1, y equals 0. So you have 2 possibilities. Okay. So, yeah. Perhaps let's just give this a name. This is called z. Okay. The new random variable. The sum is z. Big Z equals 0. There's only one possibility. And this is z equals 1. There are 2 possibilities. Z equals 2. Z equals 3. And so on. Okay, so basically we see the subscript of a and b sum up to a constant, because these are the values of x and y after all. So we can write the derivation here. The probability of x plus y equals k. Right. You can use the total probability formula, which is the sum of probability of x equals L, x equals n, okay, x equals n, y must equal to k minus n, and n ranges from 0 to k. And by independence, you can factor the probability as probability of x equals n times the probability of y equals k minus n. And of course, this is just the sum of k from 0 to n from 0 to k, and from 0 to k an times bk minus n. Okay, so that's the answer. We got the answer, right? The general formula. This is our CK. The distribution of CK is now solved. But if we look at the generating function, or the Z transform of the two probability mass function, we will see an equivalent solution in a way that is much more elegant. Okay, so yeah, this is just working with PMAT itself, but there's a method too. What does this CK stand for? Well, it has a nice interpretation for the PMF, for the PGF, or the Z transform. The Z transform, or the PGF, probability generating function, of X and Y are as follows. Okay, so we typically in probability theory we write big G of X of Z. G stands for generating. Okay, as the sum of the probability of X equals N, Z to the N, right? Because probability of X equals N is just a sequence. N goes from 0 to infinity. This is the sum of 0 to infinity, a n, z to the n, and gy of z. Yeah, new order, they formed out of the ashes of joy division. Exactly. Yeah, I'm a sucker for their music. Probability of y equals m, z to the m, equals the sum of 0 to infinity, bm, z to the n. Okay? So let's now try to multiply these two functions and see what happens. It's nothing short of a miracle. Okay, so multiplying the two series. Okay, why don't we write terms explicitly to appreciate what is happening? So here you have a0 plus a1z plus a2 z2 plus a3 z2 z cubed, and so on. And we just pretend these are polynomials, okay? And not worry about the convergence, as I said. Okay, don't worry about interchanging orders and whatnot. But typically it's fine, because for probability, these are absolutely convergent series. Okay, so you can do whichever order you want. Okay, so b1 times z plus b2 z squared plus b3 z cubed, and so on. And you just expand them as if they are polynomials, and you get what? And you get b a0 b0 plus a0. Okay, so for the linear term, you got two terms to combine, a0 b1 plus b1 a0 times z. Okay, and then for the quadratic term, you have three coefficients to combine, a0 b2 plus a1 b1 plus a2 b0 z squared. And you see the pattern. It's the same process of combining the diagonal numbers. So this is just the sum of ck z to the k from 0 to infinity, where ck is the sum of an bk minus n from 0 to infinity, and not n from 0 to k, and not to infinity. But why is this the probability of x plus y equals k then? Right? Seems like a coincidence, but of course there's no coincidence whatsoever. Gx is what? Using probabilistic notation, this is the expected value of z to the x. here, look at this definition. This is the probability mass function times a function which depends on the value of x. So that's just the expected value of that function, expected value of z to the n. So here, this in expectation notation, that's just expectation of z to the x. And here, this is the same. The generating function for y, that's the expectation of z to the y, just in expectation notation. Okay, but what is the by definition? Okay, consider the definition here. What is the definition? If this is a definition for the probability generating function, then what would be the definition for the probability generating function for the new random variable x plus y? Of course, that should be just expectation of z to the x plus y. But we know that this is just the expectation of z to the x times z to the y, factoring out just the law of exponent. But now you have a product of two functions, and x and y are independent. By independence of random variables, you can factor the expectation. Which is exactly gx times gy. So there's no mystery whatsoever. And of course, the expansion coefficient is the probability mass function of the new random variable. So what does this example tell us? The sum of two random variables has a distribution given by this formula, which is a summation. This is a relatively complicated operation, right? You need to multiply things term-wise and you add the sum together, right? I mean, it's not unintuitive, but calculating this isn't perhaps the most convenient thing. On the other hand, wow, you have an excellently simple representation for the sum of x plus y. Remember, the generating function and the probability mass function are in one-to-one correspondence. If you know the generating function, you know the PMF, and vice versa. So the distribution of x plus y is much more efficiently represented by the generating function. This is just the product of the two original PGFs or Z transforms. So you can represent this complicated operation of multiplying PMF and then summing them up in this single multiplication. And this will be called convolution. What we just did is to motivate the notion of convolution. And this is a convolution in a discrete setup. Okay. In a continuous setup, a and b are both continuous functions, or shall we say, functions of a continuous variable. And the summation is represented by integral. So this gives us a reason why we should care about this idea due to Euler, the one-to-one correspondence between the sequence and the power series. That's our first example. Okay, and which also leads to the definition of convolution down the road. Second example. And of course, this has endless application. This formula here, right here, this has endless application. This is used to study stochastic processes such as the branching process. The branching process, also known as the Galton-Watson process, to study the survival of family names. And perhaps above all else, this is used to prove central limit theorem in a classical setting. Extremely powerful tool. Anyway, next up, example 2. So now let's take a look at a second example in discrete mathematics, which is difference equations. difference equation. And perhaps the most famous difference equation is the one that defines the Fibonacci sequence. So the Fibonacci sequence, we all know what it looks like. So Fn, the sequence Fn, looks like this. The definition may vary when it comes to the initial values, but let's just take the classic one. The two initial values are 1, and the third value is the sum of the one previous two, so it's 2. And then 1 plus 2 you get 3, 2 plus 3 you get 5, 5 plus 3 plus 5 you get 8, and then 13, 21, 34, and so on. This is the Fibonacci sequence. Of course, we define it using a difference equation or recurrence relation. Okay, the problem now is to give a general formula for Fn. So F0 equals F1 equals 1, and Fn equals Fn minus 1 plus Fn minus 2 for n greater or equal to 2. This is a difference equation. This is a difference equation that defines the Fibonacci sequence. So the question now is to find an explicit formula, a closed form formula. For Fn. Okay, so how do we do that? Well, we just defined the generating function, so why don't we try that? Okay, so let's define the generating function for Fn. You know where I'm kind of going, because eventually we're going to talk about differential equation, and this difference equation is, of course, the discrete analog. So the Z transform or the generating function can solve the difference equation. By analogy, the Laplace transform solves differential equation. Okay, so I'm giving away my train of thought here. All right, so basically this is the difference equation. How do we solve the for Fn then? Well, this is how we do it. You start with defining the generating function. Let's just call it big F. Right? Call it big F of Z. Big F of Z. The Z transform is Fn times Z to the n. N goes from 0 to infinity. Okay, so we wish to come up with an encoding of sorts of the recurrence relation. So this is a sequence. How do we encode this information? Well, why don't we just substitute the recurrence relation in here? So let's do that. So Fz, you got the two initial terms, right? So you got the two initial terms, which is F0 times Z to the 0, which is a constant, and then F1 times Z plus the sum, n goes from 2 to infinity, Fn Z to the n. Okay, and when n greater or equal to 2, Fn can be represented by the recurrence relation. So let's do that substitution. So you get F0 plus F1 of Z plus the sum of n from 2 to infinity, Fn minus 1 plus Fn minus 2 times Z to the n. Okay, break the sum into 2. Oh, actually, let me just substitute the values of F0 and F1. Okay, just 1 and 1. So this is 1 plus Z plus the sum of n from 2 to infinity, Fn minus 1, Z to the n, plus the sum of fn minus 2, n from 2 to infinity z to the n. Yeah, so is it disconnected? Okay, that's odd. Something weird with the internet. Okay, so 1 plus z plus, let's change the index, because this kind of looks like the generating function, right? And the index starts from 0, so let's do that. So let's just shift the index and let n start from 0 to infinity. Oh, actually, you know what? Perhaps I should change the index so that the index for f, for little f, is just n. Okay, so fn, I want fn. Actually, I'm kind of having a trouble doing the shifting index in my head. So for the first sequence, let's write m minus 1 equals L. Always find that helpful, because sometimes I have trouble mentally shifting index. I know I'm slow. So m minus 1 is L, so n is L plus 1. Okay, so z to the L plus 1. And the new index L must start from 1. Yeah, because n start from 2, L must start from 1. 1 to infinity. Okay, so that's the first series after shifting index. And the second one, let's just do k. m minus 2, let's write it as k. So n is now k plus 2. So you have the sum of fk, z to the k plus 2, and k goes from 0 to infinity. Yeah, chat is helping me out. Okay, so and now we have to relate, right, these two new sums to f of z. There's got to be a relation here. So in the second sum, so actually in the first series on the right hand side, let's take out z, and this is L from 1 to infinity, fl z to the L. But this is only different from fz by the first term. The only this term right here is different from fz only by the n equals 0 term. So why don't we change the index L from 1 to 0 and then subtract the zeros order term, which is f0, which is 1. Okay. So this is what I did to this series. I repeat that again. So first take out the z here. And then we notice that the summation index L goes from 1 to infinity. And this is almost the same as fz, except for fz. In fz, the summation index goes from 0. So after factoring out, the series is different from fz by a constant term. So we subtract by 1. And then this way you can write this as fz minus 1. Okay, and then now for the second term, you just factor out z squared, and then the series is just k from 0 to infinity, fk z to the k, and this is just fz. So see what we have here? We end up having a equation for fz. Therefore, to summarize, you have fz equals 1 plus z plus z times fz minus 1, and then plus z squared fz. And this, of course, simplifies to 1 plus z times fz plus z squared f of z. And of course, this can be easily solved. Fz, this is just 1 over 1 minus z squared. This is f of z. So now you have f of z. It's just a matter of expanding f of z to get the coefficients fn. Well, you can use the Taylor formula, but it won't be easy to differentiate. So instead, what we're going to do is to use a trick called the partial fraction expansion. We make use of the fact that the geometric series has a well-known expansion. And by expanding this into a partial fraction, right, a common trick in elementary calculus to do integration, here we're going to use a partial fraction to expand this into geometric series, basically. Okay, so now we need, basically now you need the inverse Z transform. Now we do the inverse Z transform from the generating function to get the coefficient. Okay, to do so, we perform a partial fraction. To do a partial fraction, well, this is Calc 1 stuff. First, let's find the zeros of the denominator. So 1 minus z squared, set that to 0. And this way you get just a quadratic equation, right? Z squared plus z minus 1 equals 0. So z is, this is the root, this is the golden ratio. So it's a minus 1 plus or minus the square root of 5 over 2. So these are the golden ratios. So now we can factorize, right, the quadratic polynomial into z minus minus 1 plus or minus square root of, actually let me just write it as plus the square root of 5 over 2. Guys, what's the standard notation for the golden ratio? Or actually, what is the golden ratio? I forgot. Guys, help me out here. Let me just search it, okay? Golden ratio. I believe it's a phi. Yeah, so this is a golden ratio, so this is phi. Okay, so let me use this notation. So phi is 1 plus the square root of 5 over 2. Yeah. And the other root is what? And the other root is just phi reciprocal, right? So if I wanted to write, because minus 1 times the square root of 5 over 2 times 1 plus the square root of 5 over 2 is a 1. This is phi, and this is just the reciprocal of phi. Okay, so let's write it as z minus phi inverse times z plus phi. Oh, actually, that's not right. That's not right because this is not the original, but rather z squared plus z minus 1. Okay, so we have our factorization. Then we can write the reciprocal. 1 over z minus z squared. This is 1 over phi inverse minus z times phi plus z. Like that. Right? So we factored the denominator. Okay, and we're going to use a partial fraction expansion and say this is a over phi inverse minus z plus b over phi plus z. All right? Right, so a and b are to be determined, are constant. So you just expand this. So to do this, this is rather standard. So 1, the upstairs, okay, the numerator should be a times phi plus z, and then plus b times phi inverse minus z. Okay, and then we set z equals minus phi. This way, you get b. Set z equals minus phi, then you get 1 equals b times phi inverse plus phi. All right. So b is, can we simplify that? Can we simplify this expression for b? b is 1 over phi inverse plus phi. Can we simplify this? Actually, let's worry about that later, okay? For first, get a. So now let's set z equals phi inverse. This way, the b term gets killed. And now you just get 1 equals a times phi plus phi inverse. So a is the same thing. A is also phi plus phi inverse. Can we get the simplification going? I suspect this is simplifiable because let's write it on the side. So you have phi squared plus phi minus 1 is 0, right? So let's divide phi on both sides. Is that how you do it? Or maybe shift 1 to one side. You get phi squared plus phi equals 1. Phi squared plus phi equals 1. Divide by phi on both sides. No, you get a minus sign. That's not good. Okay, a and b are the same. Okay, so okay, let's write it this way. 1 over phi plus phi inverse is what? Multiply phi on both sides, on top and bottom, so you get phi over phi squared plus 1. Doesn't seem you can get a lot of simplification directly from the equation, so you have to, I guess, calculate the coefficients by brute force. Okay, but that's not really important here. The important part is that a and b are now found. Okay, a and b are now found. You can expand the geometric series to get the coefficients. So a is 1 over phi plus phi inverse. B is the same. So the common coefficient times 1 over phi inverse minus phi plus 1 over phi plus z. All right. So what do we want to use here? We want to use the geometric series. We want to use the geometric series, namely 1 over 1 minus z equals the sum of z to the n goes from 0 to infinity. We want to use that. So here we have two perfect candidates that almost look like a geometric series. But to do that, we need to factor out the constant. Okay, we need to factor out the constant. So the first term now becomes 1 over, if you take out the phi reciprocal, you get 1 plus phi to the minus 2. Right, and then times 1 over 1 minus z divided by phi to the minus 1, phi to the minus 1, so that's just phi z. Yeah, looks good. And the second term is you got to multiply, you got to factor out the phi. So this way you get 1 over phi squared plus 1, and then times 1 over 1 plus z over phi. So now you're ready to expand. This is 1 over 1 plus phi squared, phi to the minus 2. Okay, and then multiply by the series, n goes from 0 to infinity, phi to the n, z to the n. And here you got the second series, 1 over phi squared plus 1. The sum of phi to the minus n, actually minus phi to the minus n. Yeah, because this is a plus sign, so it should be minus phi to the minus n, z to the n from 0 to infinity. And now just combine this into a big, here, this is a big Fz, right? And just combine this into a series with a big coefficient. And that big coefficient, after some simplification, is the closed form formula for the Fibonacci sequence. Pretty amazing, right? So this is phi to the n over 1 plus phi to the minus 2, and then plus minus phi to the minus n over phi squared over 2. I'm pretty sure you can simplify this further, but I'm not going to do so. Here, essentially, we already have the answer. This is Fn. This is Fn. So this is perhaps surprising that a sequence which consists of nothing but integers will have an explicit formula with irrational numbers in there. So there's a golden ratio hidden in this sequence of integers. Okay, so which is pretty amazing. But the main lesson is that a generating function can help us solve difference equation. Let's think about why is that though? Why is that? How does this simplification happen? Why is this construction, what exactly does it help us? Where does it exactly help us? Well, where do we turn the recurrence relation into a relation for the generating function? It's here. It's here and here. This is where generating function shows up on the right hand side. So the difference equation can be encoded this way. What's that? Well, the shifted version of the sequence corresponds to just a generating function plus or minus some constant times an extra factor. So this turns shifting a linear operation into a multiplication. Does that sound familiar? A linear operation turned into multiplication? What's that? Oh, that's eigenvalue. That's eigenvalue and the idea of eigenvalue, eigenvectors. It turns a linear transformation into multiplication. Okay, and just jumping a little bit ahead. Okay, so we're going to get to Laplace transform and Fourier transform. So let's say if you have a function y of t greater or equal to 0, which will show that big Ys, which is a Laplace transform of this thing, which is defined as following: the integral from 0 to infinity y of t e to the minus s of t dt. This is a Laplace transform. The Laplace transform of y prime, differentiation in the time domain is a complicated operation, but in the s domain it's just s times ys minus y0. Does that look similar? So yeah, so basically these two examples contains the seed of the main applications. I mean, not nowadays it's not the main application, but two typical applications of the generating function. One is handle convolution in a compact way, and second is to solve differential equations, which essentially amounts to an eigenvalue decomposition. Okay, so it's a generalized eigenvalue decomposition. Anyway, so how do we go from discrete to continuous then? How do we go from discrete? This is a discrete picture. How's the continuous picture? Continuous analog of this process. Well, let's take a look at the generating function. All right, so the generating function, which is defined here, is a summation. So of course, now we wanted to, hang on, let me just, okay. We wanted to say, generalize this construction or give an analogy of this construction for a function defined on the positive real axis. This is not an is no longer a continuous object, okay? So you want to say, give an analogy for an, right? N is greater or equal to 0, to a function y of t greater or equal to 0. What would be the corresponding transformation? What would be the corresponding transformation of the power series? Well, you can think of the summation as this way: an z to the n delta n, because delta n, the increment of n, is constant 1. So this looks awfully similar to an integral. The integral from 0 to infinity. An is now replaced by y of t, and z to the n is replaced by z to the t, and then dn is replaced by dt. So that's the analogy in the continuous setup. Of course, z is just an auxiliary variable after all. There's nothing special about z. Right? You can change the exponential function with a different base, and of course in calculus we like to use base e. So you can write z as e to the natural log of z, and of course the natural log of z is also arbitrary. You can simply write it as e to the minus st. Okay, the minus sign is introduced so that functions with moderate growth, with exponential order of growth, can have a convergent integral. So that's the motivation here, with a minus sign. Of course, in probability theory, the probability density function often decays rather sharply. Not always, but things like the normal distribution, they decay rather sharply. So there's no need to put the minus sign here. So really you can just replace z to the t by another exponential. Let's write it as e to the minus z. Okay, sorry, my bad. There's no t here, but there's a t here. So you can just rewrite this as the integral from 0 to infinity y of t e to the minus s of t dt. Okay, so to write this this way, the minus sign, as I said, is to get a convergent integral for positive s when yt grows moderately, okay, in the sense that it doesn't grow faster than exponential function. This way you get an integral. This way you get a convergent integral. Okay, and in probability theory, this is exactly the Laplace transform, by the way. This is the Laplace transform of y of t. Definition of Laplace transform. Okay, and here in probability theory, because as I said, the y of t is now considered a density function. Say, for example, in probability theory, say x is a continuous random variable, say with x greater or equal to 0, like an exponential distribution, right? Chi-square distribution. These are non-negative value random variables, continuous random variable with a probability density function. is probability density function of, say, f of x, fx of x. That's the typical notation in probability theory. In that case, there's no need to use a minus sign. And actually, not using a minus sign has an advantage as well, as we will see. We define the moment generating function. MGF as follows. That's the integral. Let's call it. It typically is denoted as mx of t, which is the integral from 0 to infinity fx of little x, and then e to the t of little x, t times little x, and then dx. So here, in Laplace transform, s is the auxiliary variable, is the variable in the new function, because y of t typically in engineering represents a continuous time signal. T is time, when y is some physical quantity like voltage. All right. In probability, t is usually meaningless, so we just use t. Okay. So that's different convention, but once again, pretty much the same mathematical construction. And of course, here, moment generating function can be also defined for real valued random variables, okay, not just positive real valued random variables. Like normal distribution, you just extend the integral to minus infinity, that will do. Okay, so here I'm using positive random variables. Actually, I don't know. Let me get rid of that, actually. Yeah, there's no need for that. Just go from minus infinity to infinity. You get the idea. Right? Continuous random variable, meaning it takes real value. Okay, and then dx. Okay. So this is called a moment generating function, and in expectation notation, this would be the expectation of e to the t big X. That's the moment generating function. Okay, and why it's called a moment generating function? Well, and here's the reason for the name. Reason for it, you see, as it pretty much is the it's this essentially the same as Laplace transform in differential equation signal analysis, applied mathematics. Right? In probability and stat, we speak of moment generating function, and the reason for the name is as follows. For the name MGF is that if you say naively expand the exponential function, the expansion coefficient of the MGF as a power series in T are related to the moments. So MGF, by our definition, is the definition. Let me box that. Can be then expanded as follows. E to the tx, and you're just going to use the exponential series inside the expectation. So that's the sum of n from 0 to infinity, t to the n, over n factorial, x to the n. Only x is a random variable, t is an auxiliary variable, just constant in the sense of deterministic. Okay, so now assume this is okay. Okay, assume you can interchange the order of expectation and summation. This requires a measure theoretic justification. Dominated convergence theorem, monotone convergence theorem, one of those things. Expected value of what? X to the n over n factorial, and then t to the n. You see, so the coefficient here, as a power series expansion of the MGF, the coefficient has to do with moment, right? This is the nth moment. So that's why it's called the moment generating function. the nth moment. Okay, and of course, on the other hand, you have mx of t just by Taylor expansion or Maclaurin expansion. This is the nth order derivative evaluated as 0 over n factorial. So simply by comparing the coefficients, you get a formula which says the nth order, the nth moment of a random variable is the nth order derivative of the MGF evaluated at 0. Okay, under regularity conditions. So this is extremely helpful because calculating moment is a difficult integral typically. But if you have the moment generating function, calculating moment is simply an exercise in differentiation. Differentiation is much easier than integrals. Okay, so that's the, perhaps we should see an example of MGF. Let's see an example. Example of MGF. Why don't we take the normal distribution? Say if x follows the normal distribution with mu sigma squared, and let's calculate the MGF and find its moment. Calculate mx of t and expected value of x to the n. Let's do that. Okay, solution. So mx of t, this is, because we want to kind of bounce around between analogies and actual calculation, this way to keep things grounded. Okay, that's the expected value of e to the tx. For that, you will need a density, which we will write right now, minus infinity to infinity. The density of the normal distribution is 1 over the square root of 2 pi sigma squared. Sigma squared is in the square root. That we also seen the normal density in our earlier stochastic processes for physicists stream. The Gaussian assumption is very common over there too. Exponential to the minus x minus mu squared over 2 sigma squared times e to the tx dx. Right? So that's the definition. And the obvious manipulation is to combine the two exponents. So you get the integral from minus infinity to infinity, 1 over the square root of 2 pi sigma squared e to the minus x minus mu quantity squared over 2 sigma squared plus tx. Okay, inside the integral, t is treated as a constant basically. Only x is the variable that gets integrated. So t is just a parameter here. So looking at this, what can we say about this integral? Well, the thing is, in the density of a normal, you got a quadratic, right? You got a quadratic that is a complete square. You got a quadratic in the complete square inside the normal density, and of course we know the integral for that is 1. The integral of the density is 1. That's a normalization condition. But here, looking at the new exponent, you still have a quadratic in x, but it's not a complete square. So let's try to use that trick from high school to write the quadratic as a complete square. So you have a complete square, which is minus x to the mu, x minus a mu quantity squared over 2 sigma squared, and then plus tx. Okay, and then just do the complete square thing. Minus 1 over 2 sigma squared. Expand the square, you get x squared. Here. Yeah, let me expand the square, you get x squared minus 2 mu x plus mu squared. And then minus 2 sigma squared t times x. Right. And now we combine the linear terms, So minus 1 over 2 sigma squared. All right, and you have x squared minus 2 mu plus sigma squared times t, quantity x plus mu squared. Okay, to make this into a complete square, we need to add and subtract certain term. And let's see what's that. Well, because of the 2 times mu plus sigma squared t thing, we need to do so. We need to add mu plus sigma squared t quantity squared, and then minus mu plus sigma squared t quantity squared plus mu squared. So that's pretty much the square thing. So you got minus here 2 sigma squared x minus, okay, quantity mu minus, just write x minus mu minus sigma squared t quantity squared. This is a complete square. All right, and then do the following, which is plus 2 sigma squared. Okay, expand this square and we can, let's do this. Okay, mu plus sigma, let's do it slowly. Mu plus sigma squared t quantity squared, and then minus mu squared. So here you can also simplify this a little bit on top using the difference of square formula. This way you get 2 sigma squared. Add them together, you get 2 mu, right? 2 mu plus sigma squared t times sigma squared t. Sigma squared t. So this simplifies to 2 mu t. Yeah, expand that, you get 2 mu t, sigma squared cancels. Actually, there's no 2 here, just mu t. You get mu t plus half sigma squared t. Half sigma squared t. So that's the outcome of the completing the square. So therefore, this integral, big star is now the integral from minus infinity to infinity, 1 over the square root of 2 pi sigma squared, okay, and then times e to the minus x minus mu minus sigma squared t quantity squared over 2 sigma squared. And the nice thing about this is it has nothing to do with x. So you should add this on the end, right? So here, let's put that here, mu t plus half sigma squared t dt, dx. So because of the extra term we obtain from completing the square has nothing to do with x, you can just factor it out. You get e to the mu t plus half sigma squared t times the integral from minus infinity to infinity of what's left inside, the square root of 1 over the square root of 2 pi sigma squared times e to the minus x minus mu minus sigma squared t quantity squared over 2 sigma squared dx. But now look at what happened. The integrand is just the PDF of a Gaussian distribution. This is the PDF, compare here earlier. This is a Gaussian distribution density of normal mu sigma squared. Right. So we notice where sigma and mu play their part in the density. And here, this is just the PDF of another normal distribution. This is a PDF of the normal distribution with mean mu plus sigma squared t and the variance of sigma squared. So therefore, this big integral is just 1. So you're just use the normalization condition, and you're done. So that's just therefore the moment generating function mx of t. Mx of t is what? Is e to the mu t plus half sigma squared t. Actually, there should be a square. I missed a square here. Yeah, t squared. Amazing. Right. So that's the that's the moment generating function of the Gaussian distribution. So here you have the moment generating from the Gaussian distribution. In particular, of course, we have a special Gaussian distribution, the standard normal. In particular, usually we denote the standard normal as big Z. For Z follows normal 0, 1, the standard normal distribution, the standard normal random variable has a moment generating function of e to the, because mu is 0, so the linear term in t cancels, and the quadratic term is just half t squared. There's that. Okay? And this is perfect for Taylor expansion. Remember earlier, like we said, of course, theoretically, you can use differentiation, right? But in general, a function's nth order derivative, it's not easy to write down as a sequence in n, right? At least, I mean, you can do this for first few terms, but to get a general pattern, this only works for very special cases. So here, let's consider expanding this function. So mz of t is, you can expand that. Right, so this is e half t squared. Expand this as a power series in t to get the moment. So that's the sum of, using exponential series from calculus, half t squared to the n over n factorial, and n from 0 to infinity. Right, I hope this is correct. Yeah, so this is the sum of n from 0 to infinity, t to the 2n, t to the 2n, t times 2 to the minus n over n factorial. Right. So let's compare that with the expansion, of the Maclaurin expansion, the general Maclaurin expansion. This is supposed to be, okay, this is supposed to be the sum of k from 0 to infinity, the expected value of x to the k over k factorial. Hi, Leo. Thank you very much for joining the stream. So here we're using the moment generating function to derive. Yes, we're doing moment generating function. Yeah, because that's the probabilistic version of the Laplace transform. Okay, and then t to the k. Yeah, the secret is all the transforms are the same. Don't let the big transform lie to you, right? So as I was saying in the stream description, the fundamental idea of a transform is to map a function in a linear and one-to-one way to another vector space and represent the image in a convenient choice of basis. Right. So it's fundamentally a concept in linear algebra. But as the transform gets more exotic, to get the transform formulas to prove invertibility, you need more sophisticated machinery like complex variables and measure theory. So let's compare the two outcomes, okay? So when k equals 2n, we have to compare the coefficient. You have 2 to the minus n over n factorial equals e to the expectation of x to the k over k factorial. This way, the coefficients match. And of course, this just means expected value of x to the 2n, x to the k. Let's write it as x to the k is Kermo, thank me for what? For doing the stream. No worries, man. No worries, man. I love doing this. K factorial over 2 to the n times n factorial. And of course, this is the same as the expected value. Substitute k equals 2n, so you get x to the 2n. The mean of x to 2n is 2n factorial over 2 to the n times over n factorial. So these are the even moments of the normal distribution. Let's check. Okay, let's just do a sanity check. When n is 1, expected value of x squared. This should be, actually it should be z, my bad. I'm using z for the standard normal. Okay. Using z for the standard normal. Z to the 2n. Yeah, it's a complete agree on the change of basis perspective. Thanks a lot. So then we have, so we check z squared when n equals 1. Right? N equals 1, so you should have 2 factorial over 2 to the 1 times 1 factorial, which is exactly 1. And that's exactly true. The variance should be 1. So this is good. And it's also clear that when k is not 2n, the expected value of z to the k is just 0. Yeah, the thing is, I mean, you can tell people just on a high level and say Fourier analysis is easier to solve problems, right? Because you want to decompose a complicated signal into periodic signal that way. But still, it feels kind of arbitrary, right? Why sine and cosine in particular, right? So you see a lot of beautiful animations and stuff. But like to people who already know linear algebra, I think the best explanation is that you want to represent a function that has a one-to-one correspondence to your actual function of interest. That's one. So this way you can do the inversion. And second is to represent the image in a convenient basis. So this way the description is as efficiently as possible. Okay, no worries. Leo, thanks for dropping by. By the way, today, JC mentioned in his live, he was asking me about doing a collab stream on Twitch, I believe. But he said, like, the organizers are Twitch streamers, but they said YouTube streamers can just do YouTube. And it's likely to happen near the end of August. Just wondering if you're interested, like, just so you know. I'm pretty sure JC also messaged you. Okay, thanks for stopping by, man. Yeah, here, let's come back to the moment. If k is not even, right? If k is odd, then the moment would simply be 0. And this is completely also expected because of the symmetry of the normal distribution. The symmetry of the standard Gaussian distribution, the odd moments do need to vanish. All right, so there's that. But this is just the standard normal. How can we get back to the general normal? Can we get an expression for the general normal? The moment for the general normal? It will be complicated for sure, but at least let's try to get some pattern. Right? So for the general normal, x follows normal distribution mu sigma squared. And for a general normal distribution, you can always use a trick to relate that with a standard normal distribution. So you can represent z, you can represent x as mu plus sigma z. You can represent x equals mu plus sigma z. Actually, you can do so by checking the moment generating function. Right? Often this is usually just given as a fact in intro statistics course. Right? This is a very special property of normal distribution. An affine transformation of a normal distribution is still normal. You can actually check that using the normal distribution moment generating function, because you can do a quick check for that. Quick check. This is actually true, because consider the random variable on the right-hand side. You can calculate its moment generating function. The moment generating function of mu plus sigma z of t is the moment generating function of e to the t times mu plus sigma z. Yeah? This is just a definition. Sorry, expectation, not m. Expectation. All right? So you have e to the t mu, and then you have expected value of e to the t sigma z. But what is this thing? What is this expectation? Because we have the moment generating function for z here. The moment generating function of z is, by definition, the expected value of e to the tz. But here we have e to the t sigma z. So this is just the mgf of z, whose argument is now substituted by t sigma. So therefore you get just e to the t mu times the mgf of z evaluated at t sigma, or sigma t. But now we have you can now use the formula for mzt, and that's exactly e to the t mu times e to the half sigma squared t. And that's exactly the same as the mgf of x. This is the same as the mgf of x. So here we're using a result called the uniqueness of mgf, or what we call the fact that transforming a density to an mgf is a one-to-one operation. Right? That's the whole idea. You want to transform the function in a one-to-one manner, linearly in a one-to-one manner. Right? So now you have actually proved this result. The fact that normal random variable can be written as in terms of a standardized random variable. Okay, so here we're going to use this fact because the expected value of x to the n is now the expected value of mu plus sigma z to the n, taking expectation. And now inside, you can use the binomial theorem, which is the expected value of the sum of n choose k mu to the m minus k, sigma to the k, z to the k, and from k from 0 to n. And guess what? Because you already know the moments of z, this problem is also solved. This is the so you see this is the sum of k from 0 to n choose k, mu to the m minus k, sigma to the k, and then expected value of z to the k. But expected value of z to the k is already known. Okay, let's do a quick sanity check. What is the expected value of x squared? Well, by the formula, it should be the sum k from 0 to 2 and 2 choose k, mu to the 2 minus k, sigma to the k, and then e of z to the k, the case moment of z. So k can be 0, 1, 2, but we know that the only even order moment survives. So that's just k equals 0 and k equals 2. So you get two terms surviving, 2 choose 0, mu squared, sigma to the 0, and expected value of z to the 0, which is just, let's write it this way, expected value of z to the 0, which is just 1. And the k equals 2 term also survives, 2 choose 2. And you got mu to the 0, sigma squared, expected value of z squared. These are examples, okay? And of course, this just simplifies to mu squared. Expected value of z to the 0 is 1. Expected value of z squared is also 1. That's 1, we know that. So you just mu squared plus sigma squared, which is true, which is exactly supposed to be, because that's supposed to be the expected value of x squared plus the variance of x. So this formula works. So that's the general moment formula. General moment formula for general random variable of x. So can you imagine deriving this result by pure integration alone? Wouldn't be fun, would it? Right. This is the power of generating functions. Okay. So now, we define the Laplace transform and we define the moment generating function. And we said that earlier, right? So it's supposed to turn differentiation into multiplication. And this choice of basis, namely e to the minus t, is not arbitrary either. Let's appreciate that fact. Okay, we just did the probabilistic application, and now let's switch back to differential equation. Okay, so let's do the probabilistic, the differential equation side of the story. Right here, just like we did earlier in the Z transform, we showed an example in probability. And here we also wanted to do a differential equation. Earlier, because of the discrete setting, we only have difference equation. Here, let's do a differential equation. Okay. The reason you don't, if I do say so myself, you don't see this in university lectures, is because differential equations and probability courses are separate. Right? In a differential equation class, you learn this is the definition of a Laplace transform, and you solve a bunch of practice problems. And in probability class, you learn, okay, this is the moment generating function. You did what we just did earlier. You're likely to do what we just did earlier, like calculating moments using moment generating function. You don't see the connection between them. They're the same underlying ideas. Okay, guys, I gotta go take a leak, and I'll be back. Give me a few minutes. While I was away, I was just thinking, we introduced the notion of convolution in a discrete setting, right? We introduced the notion of convolution in a discrete setting as the sum of two random variables. What's the story in the continuous setup? They better be similar, right? Otherwise, it breaks the paradigm of the whole story. So let's check the continuous setup before we go into differential equations. So here we're still dealing with probability. So now let's take a look at the sum of two continuous random variables. Sum of two continuous random variables. Say f of x, that's the first density. And you have also y, it's another continuous random variable. Y follows the density fy of x. And the problem is to find the joint density. So not the joint density, actually, we already know they're independent. Okay, we assume they're independent not to find the joint density. We need the density of x plus y. That's what we care about. Density of x plus y. All right, and once again, let's denote x plus y as a new random variable. Let's say call it u. Okay, the new random variable. So this is a classic problem in multivariate statistics or multivariate probability theory, is that you're given two primitive or more than one primitive random variables, and you perform some transformation to it, and you're interested in a new distribution. In fact, you can argue this is most of what mathematical statistics is about. Okay, theoretical statistics has two main objectives. One, it wished to design paradigms or principles for general inferences, such as the frequentist and Bayesian paradigm. And another more practical issue is that we wish to calculate the distribution of sample statistics. What is a sample statistic? Well, a sample statistic is simply a function of the sample points. You take a sample, which may consist of a lot of data points, right? And then you can calculate a value purely from the sample without any other help. But the problem is, how does the distribution of the sample statistic look like? Like, for example, what's the distribution of the mean and the sample variance? This is a very common question. So this is the baby version of that problem. So you just have two random variables with given distribution, and you want to find the distribution of the sum. So let's find solve that problem. So there are many ways to solve this problem. A common way is to first find the CDF. We're going to use the CDF technique. Okay. So the CDF technique says, okay, we're going to first find the CDF, which is the probability of big U less than or equal to little u. And second, you want to differentiate. You just take the derivative, which is fu of little u, defined as d over du of the CDF. The reason we do that is because CDF is a probability, and just for probability, there's more rules we can use. Right. Things like the law of total probability and things like that, right? So here we have the probability of u less than or equal to little u, which is the probability of x plus y less than or equal to little u. Okay, so how can we represent this probability? Right, so here let's draw a diagram here. X and y are points on the 2D plane. And x plus y less than or equal to u, when u is fixed, represents the region under a straight line. So this is a region. This is a region we wish to calculate probability for, right? So this is the we want to calculate the probability for this region, this event, the measure of probability measure for this set. So of course, you use the integral. This is a double integral over the set x and y, coordinate x and y, such that x plus y is less than or equal to u. Of the density f of x and y, the joint density is written this way: f with a subscript x, y, x and y, dx, dy. Right. You're considering, you can perhaps, if thinking about this formula is a little bit unnatural, you can just write, this is the probability of x and y belongs to a certain region called S. Right? This is the region S. And it's written this way as a double integral. So to evaluate the double integral, of course, we use iterated integral. Okay, we use iterated integral. For example, let's just use a multivariable calculus trick. Okay, so fix x, and you integrate over y. Fix x first. Okay, integrate over y first, and then integrate over x. That's the idea. So yeah, fix x like this. And what would be the range of y? For a fixed x, then y is less than or equal to u minus x. So integrating x is from minus infinity to infinity. This is dx. Okay. The inner integral with respect to dy goes from minus infinity to u minus x. Okay, u minus x, and then what else? Well, of course, you have the inner integral and the integrand. The integrand can be written as a product, which is f of x of little x times f of y little y. Right. This is by the independence assumption. Okay, so now take a look at the inner integral. The inner integral is with respect to y, so fx can be taken out of the integral. You get the integral from minus infinity to infinity. Fx of little x, integral from minus infinity of u minus little x. Here you have fy of little y, dy, and then dx. That's it. Okay, and this is all you can say about the joint CDF. And now let's differentiate. So fu of little u is d over du, the probability of big U less than or equal to little u. Okay, and what else? This is you need to use a differentiation in the integral sign trick. So where's u? U is here, is in the upper bound of the integration. So assume you can differentiate under the integral sign. What do we have? This is something called the Leibniz rule. Leibniz rule of differentiation under the integral sign gives you minus infinity to infinity fx of x, and then fy of u minus x. Just substitute u minus x inside. Okay. Okay, so now the inner integral is killed by the differentiation. Okay, let me just write that step. Okay, so this is exchanging the order. Okay, you bring the d over du inside. Fx, the first term has nothing to do with u, so just du. Perhaps let's write partial derivative. That's usually how it's done. how it's written, d over du partial derivative of the integral minus infinity to u minus x fy of y dy dx. So here, differentiation under the integral sign kills the inner integral. And then the integrand fy is now evaluated at u minus x and then dx. So finally, therefore, you have f of x plus y of u is this. And guess what? This is the convolution for continuous, with a continuous case. Compare this with the discrete convolution, which is a sum. The discrete convolution and the continuous convolution differs only the structure. Their structure is identical, right? In the discrete convolution, you use a summation. In the continuous convolution, you use the integral. And what's important is that the index here, the index of the two functions, the two sequences taking the product, sum to a constant. And here the same thing happens here. You have the sum of the argument of the two density functions being a constant, being a u. So this is a convolution for the continuous case. This is a completely natural analogy. And what's the story for the generating function? What's the story for the moment generating function? Well, for the MGF, things are particularly simple. The MGF, which is the m plus m of x plus y, it could not be simpler. This is just the expected value of e to the t times x plus y. Use the law of exponent. You get e to the tx times e to the ty. And since x and y are independent, you can factorize the product. But this is just the product of the MGF of x times the MGF of y. Done. So convolution, this is a recurring theme. The convolution corresponds to multiplication for the generating function. You see, the derivation here is almost identical as in the discrete case. And one of the advantages of measure theory is that you can do this sort of proof for any random variable. You don't have to distinguish between discrete and continuous cases anymore. So that's actually one of the key usage of measure theory, is to provide a general framework in mathematical statistics so you don't have to prove theorem twice. And of course, there's the fact that a random variable can be neither continuous or discrete. And a simple example would be if you add a continuous random variable to a discrete random variable, well, the result is neither discrete or continuous. Right? So in standard probability, so in undergraduate probability, there is no tool for handling such things. But for measure theory, there's no such problem. Okay, so fundamental story still hasn't changed when we go from discrete to continuous. Convolution corresponds to the multiplication of generating function. And actually, because I literally cannot allow myself to not mention this, this leads to the proof of central limit theorem. This leads to the proof of central limit theorem, theorem CLT. Okay, at an elementary level, okay, which says the following. So suppose you have x1, x2, all the way to xn are IID random variables with common mean, expected value of xi equals mu, and the variance of xi equals sigma squared. They're all finite. Okay, then the central limit theorem says the sample average is approximately normal. Then the square root of n times xm bar minus mu over sigma is approximately normal. I mean, to make this rigorous, you would actually say this converges in distribution to standard normal. So this approximation, rigorously speaking, this should be so-called convergence in distribution. Okay, which we will skip the technical definition here because the overall objective of this live stream is to discuss transforms. Okay, not details in probability, as n tends to infinity for large n, basically. This is the central limit theorem. It underlies pretty much all the classical statistics. Theorem CLT. Okay, so let's look at a proof based on MGF. Based on MGF, of course, MGF imposes a restriction on the applicability because you assume the MGF exists, which essentially you're assuming existence of all moments, not just assuming the existence of mean and variance. Here, even though we only said mean and variance, that's the classical version. Here, if you're using MGF, you're actually assuming the existence of MGF as well, which is a much stronger requirement. In graduate probability, in measure theoretic probability, we instead use the so-called characteristic function, which exists for all random variables. Okay. The characteristic function is the probabilistic version of Fourier transform, which we'll get to in the later half of the stream. Actually, it's already later half, right? We start at 6:30, so it's 2 hours and a half. I better get to Fourier transform soon. Okay. At least we'll talk about the discrete Fourier transform if we don't have time for the continuous Fourier. Okay. Roman, why should I like math? You don't have to. It's a free world. You don't have to. Nobody is telling you to like anything really. I like math, and I try to show why I like math, why math is beautiful, why it's useful, but it's up to you to decide whether you like to do math. There's no pressure here. What is an integral? I don't know. Like, I mean, what sort of integral are you talking about? Riemann integral, Lebesgue integral, or stochastic integral, or something else? No, I'd be more specific, I guess. Okay, so based on the MGF, we can prove the central limit theorem, derive the central limit theorem, and here's how. So basically let's try to find the MGF of this quantity here. And by the way, where did this quantity come from? Where did this come from? So xm bar is the sample mean. It's defined as 1 over n, x1 plus all the way to xn. Okay, so we can immediately calculate its mean and variance based on the ID assumption. So expected value of xm bar by linearity is just 1 over n. Is math about the structure of quantitative mental models concept? You can say that. That's certainly a valid interpretation. Are you new to the channel? Just by any means. I mean, just want to kind of know where you're coming from. It's up to you. You don't have to answer. 1 over n times n mu is just mu. So that's the sample mean. Now you can see the sample mean is constant regardless of n. There's no approximation involved. Okay, and the variance of xm bar. I'm very new. Okay, understandable. So here, like, so first of all, welcome to the stream. And I hate to mention, but basically this channel is not meant for complete beginners. So I'm kind of assuming the audience already know calculus and linear algebra, right? Because this is a trade-off. So whenever you're making math content, you always have to assume a sort of certain background. Of course, we welcome viewers of all backgrounds. Obviously, I'm a creator after all. But to follow, let's be completely honest, if to follow most of the stuff on the channel, you already need to know, for example, not just for example, but definitely first 2 years of university level math, calculus and algebra, multivariable stuff. We've been using that quite extensively. So yeah, if you're interested in what is an integral, feel free to join the Discord server or leave a comment below after the stream ends, and I'll give you relevant materials to get started with advanced math, if that's something that you're interested in. Okay? Okay. I apologize if this answer is a little bit disappointing. Okay. So there you go. Let's calculate the variance. So 1 over n, after taking variance, gives you 1 over n squared. And then inside, because of these random variables are all independent, it's just the sum of the variance. Okay. The variance of xn. Yeah, but anyways, thanks for stopping by, Roman Viking. Thanks for stopping by. Yeah. By the way, like if you're like very, very new to math, not to the channel, if you're very, very new to the math, I strongly recommend you check out JC's channel. He's also a math streamer, as well as a YouTuber. So he has 2 channels. He does math. First of all, it's math can be a hobby. This is perhaps what he would like to promote more, actually, because he has a series for complete beginners for into advanced math. This is JC Practice Math. Yes, we all got to start somewhere. There's no shame, exactly. Exactly. There's absolutely no shame. I'm not shaming anybody, just to be clear. But as a creator, I have to assume a certain background. Like, it's okay to be completely new. Okay. I'm not shaming anybody. Okay. So if I do come off as somewhat condescending, that's not what I mean. I just wanted to emphasize that. If that's what you feel, I'm sorry. Okay. And I apologize. Okay. So I'm not trying to shame anybody. Okay. It's just that when you're a creator, you have a target audience, right? And here, like this channel, I was saying, like if you go to JC Practice Math and you go to his, actually, let me just link the Math for Beginners or something like that, math, Intro to Pure Math. So he covers things like proof writing from scratch, and he also live streams very frequently. Actually, recently he split his main channel. What I just showed was his main channel to another smaller channel called JC Practices Math. This one, Math Can Be a Hobby, is his main channel, and JC Practices Math is his live stream channel, which is currently he just started it. He just started the new channel, and go there and interact with him. And actually, where's the chat? Okay, sorry, OBS. Yeah, this one. This one. You can. He live stream. This is a live stream channel. Okay. So yeah, go ahead and yeah, he does basic mathematics there. Okay, very good stuff. Exactly. So anyway, coming back, I just calculated the mean and variance of xn bar. So basically, here what it says is this conclusion. Basically, what it says is it looks like a random expression, but basically, what it says is xn bar is approximately normal with mean mu and sigma square over n as variance. And of course, you can standardize this one and to get the expression on the left-hand side. Xn bar minus mu and divided by the standard deviation, which is sigma over the square root of n. Okay, so this is where the intuition comes from. You can already calculate the mean and variance But the CLT says, okay, this actually pretty much characterizes the entire distribution because it is normal. Normal distribution only need mean and variance. All the other information is pretty much forgotten. You can think of that way. Okay. Anyway, let me actually close off my WeChat. It's getting annoying. Anyway, just want to see if there's anything important I need to reply right away. That's fine. Nothing super important. Okay, so let's come back to the derivation of the CLT. It's a straightforward application of moment generating function. So we just want to calculate the moment generating function and then take the limit n tends to infinity. That's the idea. So yeah, the moment generating function of square root of n xm bar minus mu over sigma of t. Okay, we want to calculate that. So that's the expected value of e to the t times the square root of n over sigma times xm bar minus mu. Actually, you know what? I'm going to simplify things a little bit. This is getting too ugly, right? As you can probably agree. So let's write, okay, zi as xi minus mu over sigma. Okay, almost like a standardization, but we're not assuming xi's are normal. So zi can be some weird distribution, but this transformation is valid. Okay, this can still exist. So from there we get zi to have mean 0 and the variance of just 1. So that's the whole point of introducing zi, to simplify things, simplify the notations. Okay, so now you have square root of n xm bar minus mu over sigma. Okay, what's that? Well, this is just, let's write it as square root of n over sigma. Xm bar is the sum of xi, I from 1 to n, divided by n, okay, minus mu. All right, so here you have xi, where xi can be written as mu plus sigma zi, right? So square root of n over sigma 1 over n times here the sum of zi I from 1 to n plus sigma mu. Not sigma mu. Yeah, sigma. No, this is not a good idea. This is my bad. Mu plus sigma zi. And then minus mu. So you end up getting square root of n over sigma times 1 over n, right? And then n times mu plus sigma times sum of zi, I from 1 to n, and then minus mu. So mu cancels and sigma cancels, so you just get the square root of n times the sigma of zi, I from 1 to n. See, mu cancels. Oh, actually, never mind. There's n at the bottom, so you just get 1 over square root of n. Yeah, this is 1 over square root of n. Much better. This is a lot simpler than this. Right? There's no parameters mu sigma involved. So we like this a lot better than this one. Their equivalent expression. Excellent. So MGF of the random variable of interest is now the MGF of this thing, 1 over the square root of n, sum of zi. Okay, and what's the definition of MGF? Well, that's just the expected value of e to the t 1 over square root of n, the sum of zi, I from 1 to n. Okay, and then use the law of exponent. Inside is a product. The product of 1 to n, product from I from 1 to n, exponential of t over square root of n, zi. Just the law of exponent. And now because of zi's are IID, xi's are IID, so zi's are IID as well. Because each zi only depends on xi. xi IID, zi IID. So you can factor the exponential, factor the product, factor the expected value. Sorry, I can't speak. Product of the expected value I from 1 to n, e to the t over square root of n zi. But what is this? This is the MGF of zi. This is the MGF of zi evaluated at t over square root of n. This is the definition of MGF of zi, but evaluated at t over square root of n. Well, what can we say about this? Because zi's are all IID, right? xi's are IID, zi's must be IID, because the same transformation applied to each xi. These are IID random variables. So therefore, this is just the MGF of zi raised to the power t over square root of n raised to the power of n. They're all the same. And now can we say something about the inside? Remember earlier we have the MGF as a power series expansion. Here, MGF as a power series expansion, right here. MGF is a power series expansion in which the coefficients are related to the moment. Let's apply that right now. Okay, so here inside, this is the summation of k from 0 to infinity, expected value of x to the k over k factorial, okay, k factorial, and then t over square root of n raised to the k. This looks horrendous, I know, but it's going to simplify very soon. Okay, so yeah, raised to the n. But now, what's happening inside? Oh, let me write, this is not x, but zi. You've seen this expansion earlier. So, what are the first few terms? The zeroth order term is always 1. Is always 1. When k equals 0, this power is 1. The coefficient is e to the z to the 0, which is 1, over 0 factorial, which is 1. So the zeroth order term is just 1. When k equals 1, the term vanishes, because e of zi is 0. We designed zi specifically to make sure the first order moment vanish. And then when you let k equals 2, you get the second moment on top. Second moment is 1. Second moment equals variance in this case. So that's just 1 over 2 factorial. And then you have what? T squared over n. And then plus what? Plus higher order terms. Plus higher order terms of t squared over n. Little o, t squared over n. Raised to the power of n. But this is exactly the exponential series, exponential limit. So we all know from calculus that the limit of 1 plus x over n raised to the n power, n tends to infinity, is e to the x. Everyone knows that from calculus. But In fact, if you add higher order terms of x to the n, of x over n, so if you add higher order terms, so little o of x over n, it won't change a thing. It is still e to the x. This is the important result. So after n tends to infinity, this is just e to the, this is just, now look at x. X is t squared over 2. So this is half t squared, e to the 2 squared. And guess what? This is the MGF of normal 0, 1. So we're done. This completes the proof. Beautiful, isn't it? So basically, here we said this, in this little o, in this little higher order term, it would contain higher order moments of z. That is to say, higher order moments of xi. They are all forgotten here. They don't matter. So after you take the average of the sample as n tends to infinity, all the higher order moments are ignored. They don't matter here. That's the essence of the central limit theorem. Okay, yeah. So I think this is enough probability, right? So this is enough probability. Let's come back to differential equation. Let's come back to differential equation and see how Laplace transform make our lives easier. Okay, so I might need to draw some separation line here. This is a continuous analog. Continuous analog here, we did a bunch of probability stuff. Calculating moment, sum of random variables, as well as central limit theorem. Okay, and now let's come back to differential equation. So the idea is, can we turn differential equation into algebraic equation? How to turn, okay, differential equations into algebraic equation. So you don't need to worry about don't need to worry about calculus, right? Just do algebra. Can we do that? Well, let's take a look at a simple differential equation, which is the harmonic oscillator. Very famous in physics. Right? How do you turn differential equation into algebraic equation? So as a motivating example, let's consider the harmonic oscillator. M is the mass. This is x. Okay, suppose 0 is the equilibrium position. Then by Newton's second law, equation of motion, mass times acceleration, so basically x times mass times x double dot is minus kx. So there's that. Okay, and we can rewrite this, as usually the case in numerical method of differential equation, is that we want to write this as a system. Write this as a system of differential equations, system of DEs. And we typically do it this way. So we let x1 to be x, and x1 dot, first order time derivative, to be x2. Okay? So this way we have a system. First of all, you already have one differential equation, which is x1 dot equals x2. This one is by design. Wendelin, actually Lagrange transform is something different. This is not Lagrange transform. Perhaps we will talk about Lagrange transform in a separate stream, either called Lagrange transform or simply, or as a part of calculus of variation. The idea is a little bit different. Okay. Okay. Lagrange transform is also highly interesting, but not as an integral transform. So x1 dot is x2, and x2 dot is what? x2 dot, because x2 dot is x1 double dot. x2 dot is immediately x1 double dot, which is just x double dot. And of course, x double dot from the differential equation is minus k over m times x, which is x1. So this is x1. So we can write this as a vector equation. Okay, so you can write it as vector equation, that is x1, x2, taking time derivative, x1 dot, x2 dot as a vector, okay, equals the matrix multiplication. Matrix multiply the vector x1, x2. And in the first row, you just have x2, so the coefficient for x1 is 0, coefficient for x2 is 1. On the second row, you have minus k over m as a coefficient for x1, and there's no x2, so there's just 0. Okay, so if we write as a matrix form, so this is x1, okay, this is x1, hang on a second. Oops. X vector as x1, x2. Of course, this is time dependent, okay? X is a time dependent vector. So basically, this is a trajectory, this is a curve in the x1, x2 plane called the phase space in classical mechanics, Hamiltonian mechanics in particular. This is x, is a vector. And write A as a matrix. So A is 0, 1, minus k over m, and 0. It's a constant matrix, constant 2 by 2 matrix, and we have x vector dot equals A times x vector. So in applied mathematics, you often see this kind of linear system. So how can we solve this in general? Right? This is just an example from the harmonic oscillator. In general, for example, you can introduce damping and you will still get a system of this form. Linear damping. Okay, you can introduce, for example, add a linear damping like a piston to it. Right? This will be a model of a car suspension. So how do we solve this? Right? This is a crucial idea here. This idea is all based on the operator A, the eigenvalue of the vector A. So the idea of solution is an eigenvector expansion. How does that work? The idea of that solution is an eigenexpansion. So let's consider you have. Oh, thank you very much. Thank you very much, chat. But I still have a lot to like improve in terms of my knowledge and my teaching and all those things. But thank you. Appreciate the compliment. So the eigenexpansion as follows. So let's assume you have A has eigenvalue lambda, okay, has assume, let's just say, perhaps this is not the best way to phrase it, assuming lambda is an eigenvalue of A. Of big A, with associated eigenvector V. And then what happens? with associated eigenvector v, then by definition of from linear algebra, right? So AV is lambda v. The idea is it turns a linear operator, a matrix, the action of that matrix into multiplication, just scalar multiplication, which is a lot easier to calculate. Okay, and once you have that, you immediately have a solution. Let's see why. Claim. Then, if you have lambda and v, then immediately x equals e to the lambda t times v is a solution. So what would that solution be like? So here, in this differential equation, here we have a 2x2 system. Right? So here we have a 2x2 system, but basically, what this 2x2 system says is that on the right-hand side you have a vector field. Because x maps to ax is a vector field. At each position x, remember, is just a vector x1, x2. For each vector, you specify a position, and for that you have a new vector assigned to it, ax. So basically you have a vector field whose value at position x is ax. At each point, I mean, this is not the harmonic oscillator scenario, but okay. The thing is, I'm just giving the general idea. For a general vector ODE, x dot equals ax, what we're dealing with is the right-hand side defines a vector field. And here, what we're saying is the tangent vector x dot follows that direction, follows the direction of the vector field. So you get an integral curve as a solution. At each point on the curve, the tangent vector is tangent to the vector field. This is a solution, x of t. It's an integral curve. Kind of like the force field in classical mechanics, like gravitational force field, electrical force field. And the solution is just a force line. And here we have an eigenvector. What does that mean? It means that the action given by the vector field is in the direction of the position vector. So here, this equation says for position v, okay, this is a v, an arbitrary v, the vector field at that point is just a multiple of v. So the vector field vector is in the same direction as the position vector. And therefore, the tangent vector is in that same position, and as a result, you get a solution on a straight line. This is a very special solution, straight line solution. Right? Based on the geometric meaning of the ODE, this must be a straight line. And here exactly what we have is a straight line, because e to the lambda t is a scalar times v, you get a straight line in the direction of v, exactly as geometry predicted. This gives us a solution for free. Gives a solution immediately if you have the eigenvector. Okay, let's verify. X equals x of t, okay, x of t equals e to the lambda t times v is a solution. And let's see why. Indeed, let's differentiate, plug this into the differential equation and check. X dot of t is lambda, because you're differentiating, here, let me write it this way, is d over dt e to the lambda t times v. Right? V is a constant vector, So differentiation does not affect it. So you just differentiate the exponential to lambda e to the lambda t times v. But lambda is a constant. Lambda is a scalar. You can move it wherever you like. So now let's exchange the order. To put e to lambda t up front and lambda v here. What is lambda v? Lambda v is just av. E to lambda t times av now. But e to the lambda t is a scalar. You can move it to a new position. So this is just a e to the lambda t times v. But e to the lambda t times v is exactly x. So therefore this is ax. Therefore d is satisfied. X dot is ax. So indeed this is a solution. Okay, so for an ODE, you get this solution for free once you know the eigenvalue and eigenvector. But now, let's assume that A is quote-unquote diagonalizable, meaning it has a full set of eigenvectors. The eigenvectors of A form a basis of the vector space on which A is defined. For example, here A is 2 by 2. If A has two linearly independent eigenvectors, then we say A is diagonalizable. So if, say, A is m by n, and assume A is diagonalizable, the crucial notion from linear algebra, A is diagonalizable, then you would have a basis. Then A has, you can say there exists eigenvectors. Can you respond? Sorry, did you ask a question earlier? Subhack, I'm sorry. Did I miss you? Did I miss your message earlier? I can't see it from here, but yeah, of course I can respond. I've been always respond to chat, like every now and then when I take a break from the derivation, but I do respond. There exists eigenbases. This should be eigenvectors. And eigenvectors v1 all the way to vn that are linearly independent. So this way, this is called eigenbasis. Together, they're called an eigenbasis. Eigenvectors of A. Okay. So this is not an arbitrary choice. It is dictated by the linear operator A, or matrix A. Eigenvectors of A that are linearly independent, and this is called an eigenbasis. So, therefore, you have AI, not AI, but A lambda I equals, not A lambda I, what am I doing? A VI equals lambda I VI. A VI equals lambda I VI. I equals 1, 2, and so on. Okay, and each of them will lead to a solution. Each of them will lead to a solution, namely xi equals e to the lambda I t vi is a solution. Same reason as earlier. Okay, so now let's consider an arbitrary initial condition. For an arbitrary initial condition, x of 0 equals, say, x naught. What we can do is following. We can always expand a vector with respect to a basis. Do eigen expansion. the fundamental idea in linear algebra. You always wanted to express a vector in some convenient basis choice. So x naught eigenexpansion now reads C1 V1 plus all the way to Cn Vn. Okay, so now you have expanded the initial condition. What would be the solution then? Well, the solution to the initial value problem, okay, this is the initial value problem, x dot equals ax, and together with these two together are called initial value problem, is what? This is immediate. Once you've done the expansion, the solution is immediate because this is just x of t equals c1 e to the lambda 1t plus all the way to cn e to the lambda nt. Now, I'm really interested in the subject and how cosine and sine can be eigenvectors for real impulse response for system of Laplace transform. Okay, I think you're talking about Fourier transform, right? If we're sine and cosine, we're talking about sine and cosine. These are for Fourier transform. So this is what we have. This is the general solution. So the solution is now represented in a convenient basis choice. These are, okay, I forgot the V's, my bad. V1 plus all the way to Vn. Okay, and so this is what we mean by eigenexpansion. What we put eigenvectors, what if we, oh, by the way, here, what we just want to say is why this is a solution? Because of the existence and uniqueness theorem. A linear combination of the solutions is always a solution because the D is linear. That's obvious. And also when t equals 0, this happens to be the initial condition. So this is a solution. Okay? And assuming everything is, we have this, the assumption we did earlier, okay, it's diagonalizable and whatnot. What if we put eigenvectors in place of C1, C2, etc.? Well, C here is the coordinate. Okay, the eigenexpansion, let me draw a picture, okay? So, for example, this is R2. So this is the direction of V1, and this is the direction of V2. Right? For an arbitrary vector, x, you can expand relative to these spaces. So this is C1, V1, and this is C2, V2. C1 and C2 are not eigen. The question doesn't seem to make sense because C1 and C2 are coordinates. V are vectors, okay? Once you have chosen eigenbasis, you can calculate coordinates. Okay, so this is the idea of eigenexpansion. But now come back to Laplace transform. Right? The idea is here, we turn an operator into multiplication through eigenvalue, eigenexpansion. So the differential operator d equals dt, what is the eigenfunction of this? What is the eigenfunction of this thing? What is the eigenfunction of this thing? This is just exponential because d over dt e to the minus st is minus s e to the minus st. So this is an operator acting on a function, and the result is a multiplication. The answer is exponential. So the Laplace transform is a superposition of exponential, the continuous superposition. definition of Laplace transform that we saw earlier. First, we define the Laplace transform through analogy from the discrete case, right? But now you can think of it as a expansion. Here, yt is the coefficient. It is a continuous spectrum of coefficient. Here, in our vector ODE situation, you only have discrete coefficient because it lives in a finite dimensional space. A function lives in an infinite dimensional space. So the expansion coefficient is now a continuum. Definition of Laplace transform can be seen as eigenexpansion. So yt taking Laplace transform is the integral from 0 to infinity y of t e to the minus st dt. This is a superposition, a continuous superposition of eigenfunctions. Namely the exponential. I'm sorry, please read eigenvalues in place of C1 and C. Well, eigenvalues don't play the role of coordinates. Eigenvalue plays the role here. Okay, to do eigenexpansion, you don't need eigenvalues. The eigenvalue dictates time evolution. Here, just like you say minus s is the eigenvalue, but this is just the superposition of the eigenfunction. This is the intuition, another intuition. Because differential operator has an eigenfunction that is exponential. The answer is, the question for this one is eigenfunction of the d over dt is exponential, and here we do a superposition of exponential. And let's think about what happens when you differentiate. Okay, so if we take this as definition, we can get the next property, namely Laplace transform of derivative. Remember, eigenvalue is valuable because it turns a linear operator into scalar multiplication. Here, let's think about what does Laplace transform do to derivative. Well, it turns out is s times y of s minus y0, where y of s is the Laplace transform of y of t itself. This is the property which we'll prove right now. Okay, so the Laplace transform of y of t is the integral from 0 to infinity y prime of t e to the minus st dt. But look at y prime of t and dt. This begs for integration by part. So this is the integral from 0 to infinity e to the minus st dy dyt. So integration by part, integration by parts. Okay, you get yt times e to the minus t, 0 to infinity, and then minus the integral from 0 to infinity, here, minus to infinity, and then you have yt and d of e to the minus st. Okay, now let's evaluate. So the upper bound is the limit as t tends to infinity, y of t times e to the minus st, which we assume to be 0. So basically, the idea is we assume there exists s, eventually, we assume there exists s, okay, so that e to the st will grow faster than yt. Okay, we assume that y is sub-exponential, or at the same order of exponential. So there's that, and minus when t equals 0, this is assumed to be 0, assumed. And when t equals 0, you just get y0. And taking the differential of exponential, this is easy. So this is just integral from minus infinity y of t minus s e to the minus s of t dt. Right? So therefore, this way you just get s times integral from 0 to infinity y of t e to the minus s of t dt, and then plus y minus y0. So therefore, this is, as we can recognize, this is just y, the big Y of s. So we're done. This is the important property. So as you can see, taking the derivative corresponds to multiplying the generating function, multiplying the characteristic function by s. Right. Analogy for that in a discrete case is apparent in our Fibonacci sequence example. So in the Fibonacci sequence, we define the generating function as a power series. And here we're dealing with a shift. Right? So in the recurrence relation, you see here we have fm minus 1. And fm minus 1, if we do the manipulation here we see what we have here. You have z times big F of z minus f of 0. This is a direct analog of the continuous situation. So let's just see what we've done here. Okay, we started with an ODE example. We started with an ODE example that is eigenfunction expansion. This turns a calculus problem into a linear algebra problem. Once you solve the eigenvalue problem, the solution is immediate. Right? And even for initial conditions that aren't eigenvalues, you can do the eigenexpansion. So once again, this is again the linear algebra problem. No calculus whatsoever. Right? Start with a vector, decompose the vector onto coordinates, right? Onto subspaces, whatever you want to call it. With respect to a basis, you get the coordinate, and then solution is immediately given. Right. So here we're just going to take, once again, an analogy into the continuous situation. What is the eigenfunction of the differential operator? The eigenfunction of the differential operator is exponential. So here, well, you just take the continuous superposition of eigenfunction as the Laplace transform. So now you have a second motivation for Laplace transform, and not just from a discrete scenario, as a power series analog. Right here, this property tells us you can convert differentiation into simply multiplication. Okay, and earlier there was a question that says, how does this correspond to the linearly time invariant system, which is a great question. Okay, so for a linearly time invariant system, there are two ways to describe it. Now, in a general way, linearly time invariant system is a black box. First of all, it's a linear transformation. Okay, linear time invariant system. Time invariant linear system. Okay, what's the intuition of this system? You have an input, right, and the system gives you an output. Let's call the transformation big T. Okay, output. A typical example of that is a differential equation. Say y prime equals ay plus ay equals f of t. This is an example. Here y is considered as the output, and f is the input. F is the input. So, for example, this can model a Newton's cooling law. For example, y can stand for temperature of an object. Okay, and A dictates the rate of cooling, natural rate of cooling. If there's no heat source, and how fast does the object cool down? And f of t is an extra heat source, or sink. So it's natural to think of f as an input and y as an output. Okay, so let's first just solve the differential equation the normal way, without any reference to Laplace transform, and let's see the Laplace transform side of the story. Okay, so here, this is just an example, but the defining characteristic of the linear time invariant system is that if you delay the input by a certain amount of time, the output also delays by a certain amount of time. The amount of delay, the amount of time delay in the output is the same as the amount of time delay in the input. That's the notion of time invariance. Okay, so time invariance okay, this is time shift in input and output are always identical. Okay, and linearity is what? Linearity is well, you t of c1, let's say f1 plus c2 f2 equals c1 t of f1. It's just a definition of linearity from linear algebra. Okay. Namely, it satisfies the superposition principle. Freaking bug in my room. Superposition principle. Okay, so actually from these two properties, right, from these two defining characteristics, you can actually give the general form of a time invariant linear system. How? Let's once again use an analogy. So first let's look at a discrete case. Right? So let's say your input is an, output is bn. What would be a general linear transformation? Well, we all know from linear algebra, linear transformation is a matrix multiplication. So bn, the output can be written as the sum of C matrix multiplication. C, I would like to put C as the coefficient in the matrix, the elements in the matrix. So the matrix multiplication formula is what? C11, C12, C21, C22. I forgot the matrix multiplication formula. Okay, A1, A2. Okay, A and K. AK. There's that. Okay, so basically you need a double indexed array to define a linear transformation. This is a discrete case. Linearity implies this form. Linearity tells us Bm must be this form, sum over k. What about time invariance? Ti. Ti tells us this double indexed array in fact only has 1 degrees of freedom. Not 2 degrees of freedom, but just 1. Bn just supposed to be the not just C and K, okay, not 2 degrees of freedom, but rather another single index, C m minus k ak. Sum over k. So this way, if a is shifted by the same amount, bn is also shifted by the same amount. So the single indexed array takes over of the double indexed array. And now for the continuous case, what's the continuous analog for matrix multiplication? Input is f of t, output is y of t. So once again, linearity restricts the form of the formula. So y of t, the analog for summation, is an integral. Is an integral of a function, let's call it k, okay? K of t and s, f of s. This is an analog for matrix multiplication integrated with respect to ds. And now time invariance is imposed. So y of t is what? Is the integral of k. And now k is only a single variable function. And it only depends on the time difference. Right? This is intuitive because if it only depends on the time difference, then the starting point don't matter. If you shift the starting point in the input, the same amount of time is shifted in the output. But this is exactly a convolution, which we introduced earlier. And what does convolution do? Convolution corresponds to a multiplication for the generating function, for the probability generating function, for the moment generating function, and for, of course, for the Laplace transform. Right? And here let's look at an example, a linear ODE, inhomogeneous ODE. Okay, let's first solve it the usual way. So these aren't just arbitrary formulas, okay? The structure is imposed by the system requirement. Solution is as follows. So there are two ways to solve this. First, you have the usual way, time domain method. So the time domain method is usually you multiply by integrating factor. So the integrating factor, which is the trickery, right? So integrating factor is integral e to the integral of adt. So that's just e to the at. Yeah, it is really pleasurable, right? So that's why the stream is called the joy of integral transform. Right? So yeah, the file is getting a little bit long, so things are a little bit laggy now. I'll try to be careful. Integrating factor, first we multiply integrating factor on both sides. What do we have? Well, you get y prime e to the at plus a e to the at times y, and then e to the at f of t. Okay, so integrating factor always turns the left-hand side into a product rule. So that's d over dt y e to the at product, okay, and equals e to the at f of t. Okay, and why don't we also add an initial condition? So initial condition y0 equals y0. Okay, and then we integrate both sides from 0 to t. So you get y of t e to the a of t minus y of 0, which is just y0. Okay, time e to the 0. So that's just 1. Okay, so in the right hand side you get the integral from 0 to t e to the as fs ds, f of s ds. Okay, so let's get the output. So that's y of 0 times e to the at, e to the minus at, rearrange to get the final output. Okay, and then plus the e to the minus at, integral from 0 to t e to the as f of s ds. So you can write this as y0 e to the minus at plus the integral from 0 to t e to the minus a of t minus s f of s ds. And guess what? This is the convolution. Convolution, namely this on the right hand side, you get a linearly. This is a what we call time invariant linear system. Convolution slash TIL system. And in particular, when y0 is 0, okay, if you set y is 0, you get a convolution or TIL system. Right? So that's the system diagram here. You input f, you get output y. If the input is delayed by a certain amount of time, the output is also delayed by the same amount of time. Okay, so that's the time domain method. And what's the Laplace transform method? Well, Laplace transform method turns the differential equation into just plain algebra. Let's see how that's done. So take this is differential equation y prime plus ay equals f of t. Okay, let's denote the Laplace transform of y, little y, as big Y of s, the Laplace transform of little f as big F of s, and what we have, taking the Laplace transform on both sides, so y prime now becomes s times big Ys minus y naught. Okay, and just for the sake of simplification, let's set y naught to be 0. Okay, set y naught to be 0. So the first term is the so-called natural response, right? If there is no forcing term, if purely you have a non-zero initial condition, you get an exponential decay, obviously. So the first term is a natural response, and then you add the response given by the TIL system. Okay, and then a times the y of s, since Laplace transform is a linear transformation, equals big F of s. So you now set y naught equals 0, therefore you get s plus a big Y of s, and then equals big F of s. So y of s is what? Is 1 over s plus a times f of s. Okay, but what is this saying? This is the Laplace transform of the exponential, right? We should probably calculate it. So 1 over s plus a is the Laplace transform, but this is the Laplace transform of e to the minus at. Just do a quick calculation. The Laplace transform of e to the minus at, by definition, is the integral from 0 to infinity e to the minus st times e to the minus at dt. This, of course, is elementary. Integral e to the minus s plus a times t dt. This is just e to the minus s plus a times t over s minus s plus a. Goes from 0 to infinity. And this simplifies to 1 over s plus a. So you get a multiplication of two functions in the s domain. And as a result, we already know what happens, right? So in the time domain, this corresponds to a convolution. So here, 1 over s plus a is completely determined by the left-hand side of the dE. It has nothing to do with f of t. So this function can be seen as a characterization of that black box. F of t, big F of s is the input, the output is ys. 1 over s plus a serves as the role of the black box. So that's called a transfer function. It isolates the effect of the black box. It has nothing to do with the input. This is the transfer function. And of course, we know, well, if you take the inversion, then you get the Laplace, you can take the inverse Laplace transform. Little y is the convolution. Right? Here, inverse Laplace transform, we have not yet given a formula, because inverse Laplace transform, if you write it as a formula, you would need complex variables. So here we're just going to use the fact, the big theorem which we have stated but never proven, that Laplace transform is 1-to-1. Okay, for example, here we know the Laplace transform of the exponential is 1 over s plus a. We can immediately say the inverse Laplace transform is the original function. There's no loss of information. So this is just a convolution of, the convolution of e to the minus at minus s f of s ds. So this is why Laplace transform is naturally suited to describe TIL system. TIL system, by its very system constraint, is a convolution, and convolution corresponds to multiplication with the transfer function. Okay, so it's used for solving DEs. Okay, and for the last part, because I didn't have time to, I originally planned to discuss how to solve PDE using Fourier transform, but we didn't have time, or we won't have time to do so. But at the very least, I want to introduce Fourier transform. Okay, I want to, any questions so far, by the way? How things are defined, why we do this and that, feel free. Mathematics to signals and system. How do you do all this? How do you remember all this? I don't remember all this. I mean, I guess I memorize the definitions, and I don't memorize formula. Because you see, I don't remember the Laplace transform table, for example. If I haven't practiced it for a long time, I won't remember much of the formulas in the table. But the fundamental idea, as I said earlier, this is unforgettable, right? That's the first thing I put in the stream description. Do I still have that? Yeah, I still have that. The fundamental idea is unforgettable. The overarching idea of all kinds of integral transform is to linearly map a function in a one-to-one manner into another vector space and then represent the image with respect to some convenient basis. This is about basis. Actually, you know what, guys? Let me do a simple, super simple example to illustrate this idea again. Okay? Perhaps we will do this and we'll introduce the discrete Fourier transform to hammer this idea home. Okay? Why don't we look at the AC theory? Here, Oliver Heaviside and AC theory. Can we copy his picture here? Because he is really the person who put Laplace transform, not Laplace, okay, but really Heaviside. He put the method of operational mathematics and integral transform. Okay, I can't put it here anyway, it does not matter. Oliver Heaviside, okay? I think I've made that idea pretty clear. So Oliver Heaviside made his career as electrical engineers, completely self-learned. He was very poor throughout his whole life. Even after he made a great number of inventions, he was still very poor because of his personality, among other things, and his difficulty with the establishment, with the academic establishment. So basically, mathematicians thought his methods were not rigorous, and he had great contempt towards so-called rigorous mathematics. He had a famous quote, says, "I do not need to understand the digestion to enjoy the dinner," right? So he just does his own mathematics and ignored the criticism from mainstream mathematics, which was turning into this hyper-rigorous framework. You know, he invented the math for analyzing circuits and stuff, while analysis was considered the crown jewel, right? Real analysis, existence and uniqueness of solutions, differential equations are considered the crown jewel of mathematics. Right? He pretty much ignored everything and did his own thing, right? And called it operational mathematics. Anyway, so Oliver Heaviside and AC theory. In particular, he introduced complex numbers into AC theory. And really, what is this about? How can we represent, so to say, how can we represent the circuits using complex number? In complex number. Without diving into too much domain knowledge, but basically we can just consider three kinds of a device. Okay, so you have the resistor. So resistor satisfies the Ohm's law. Right? I is V over R. This is the resistor. Okay, and now for a capacitor like this, C, I is dV is C times dV over dt. Okay, so it's a derivative. Okay, and now next you have also the inductor. Okay, without diving into the physics, okay, we're just going to discuss mathematics here. This is how they work. This is the formula. And all of those devices can be connected in a complex network. That's all I get to say about that. Okay, the inductor, for the inductor, V is what? V is L times di over dt. You see, now capacitor is differentiation of a voltage gives you the current. For the inductor, it's differentiation of the current that gives you the voltage. So it's like an inverse operation, right? And of course, because we're dealing with AC, the voltage is sinusoidal. For AC, V of t is sinusoidal. It's like this. So it's A times omega cosine of omega t plus B times sine of omega t. Right? Okay. So what are we doing here? Well, this sort of function, this is a finite dimensional vector space. Even though the functions are continuous. Right? The function, in general, continuous function lives in a finite dimensional vector space. Lives in an infinite dimensional vector space. This lives in a finite dimensional vector space. That is the span of a cosine of omega t and sine of omega t. And what is the operator d over dt do? Operator d equals d over dt does to this vector space. This is a linear operator on the span of, let's just call it v, okay? Let's just call this, perhaps not v because v is already voltage. Give it a name. Let's give this a name. Call it vector space w, okay? Or w, on w. W is a two-dimensional vector space. And its matrix. Well, what is the general form of a matrix representation on a vector space? So a matrix representation relative to a basis of the vector space. Yeah, just shift the phase. I know but how do you get that, right? How do you get that? It's a linear algebra thing. So this is the general result from linear algebra. So let's say V is a vector space. V has basis V1 all the way to Vn. A is a linear operator from V to V. The matrix of A is as follows. Is the action of A on the basis vector and then take the coordinate relative to the basis. Okay, so for a vector x, if x is in V, then x coordinate is C1 all the way to Cn, where the C1 and Cn are unique coefficients such that x equals C1 V1 plus all the way to Cn Va. This is just linear algebra, okay? So here I'm using the formula in the middle here. The matrix representation of a vector relative to a basis. So here you have two basis vectors, cosine omega t and I omega t. So d acting on cosine omega t is just minus omega sine omega t. And therefore the coordinate of d cosine omega t is what? Is 0 minus omega. Because this has no cosine and the sine coefficient for sine is minus omega. And what happened to sine is omega times cosine. What's the coordinate for that? It's immediate, right? So it's just omega and 0. So therefore, the matrix for D is these two columns, okay? 0 minus omega and omega 0. How can we describe, so how can we make the operation of D easier? We diagonalize D. Let's calculate the eigenvalues, okay? So let's calculate the determinant of D minus lambda, the usual recipe for calculating eigenvalues. This is the determinant of minus lambda omega minus omega minus omega, which is lambda squared. I can't imagine more than two basis vector, i.e. cap and j cap. Can you explain a little bit more about basis? Okay, cool. Actually, let me go to my go-to linear algebra resource, University of Waterloo, linear algebra 1. I should make a live stream about this resource because I really like it. I mean, of course, personal bias. So anyway, but yeah, it has what we need. So I put the link in chat, okay? So here, go to matrix and linear mappings. Linear mapping of vector spaces. Where is, yeah, diagonalization. Yes, matrix of a linear map here. Matrix of a linear map. If you have a basis and a linear map, you can represent the matrix in the coordinate, and this is the derivation. Yes, this is the 90 degree. We'll derive that. We will derive that, right? So why is that, right? So here, this is the derivation. So you want the identity Lx equals matrix Lb times xb to hold. xb is the coordinate vector. So for x having this basis expansion, coefficients b1 all the way to bn together forms the column vector. That's the coordinate vector. So x can be an abstract vector. L can be an abstract linear map. But with the aid of a basis, you can convert everything into column vectors and matrices. So this is the formula that we just stated. The action of L onto the basis vector, and then take, because these are abstract vectors after all, right? These are abstract vectors in general. And then you want to take the coordinates relative to the basis. So this way they all turn into coordinate vectors. And now you just concatenate them together into a matrix. And I believe there you have examples here. So for example, this is a second example. So now, yeah, do we have like a slightly simpler example? Yeah, so if you have, say, b equals v1, v2, v3, this is the basis, and this is L. L does the following to all the basis vector. So what does that mean? So the coordinate of LV1 relative to B is just 2, minus 1, 3. 2, minus 1, 3. Yeah, and then 4, 3, minus 1. 0, minus 1, 0. Look at the solution. This is the matrix I was talking about. You put the columns together like this. Okay, so there's that. I mean, we have this representation of an abstract linear operator with respect to an abstract vector space. You can always do this using this formula here. Definition. If B equals B1 all the way to Vn is a basis for R to the n, and L from Rn to Rn is a linear operator, they don't have to be Rn, okay? It just has to be the same vector space, V. And then the matrix of L here, this is the quantity. The matrix of L with respect to the basis B is defined in a matrix whose columns are the B coordinate vectors of the images of vectors under L. See, you first take the linear transformation and act it on all the basis vector. And for each image, you take the coordinate with respect to the same basis. And following this definition, you turn any matrix transformation, you turn any linear transformation into a matrix multiplication, matrix vector multiplication. There's that. Yeah, the plural basis is basis. I saw plural basis is BASES. Okay? So anyway, here we have, we're just going to apply this formula to the derivative operator on the space spanned by cosine and sine. And this is the matrix. And what does this matrix do? Well, let's look at the eigenvector. So here, the eigenvalue in the middle of calculation, lambda squared plus omega squared equals 0. So lambda is plus or minus I omega. So that's the eigenvalue. So this says that d of the eigenvectors, as we said earlier, differential operator here, differential operator, as we said earlier, differential operator always have the exponential function as its eigenfunction. Differential operator always has exponential function as its eigenfunction. So now the eigenvalue minus s is calculated. So basically now we can write the following. So this is the eigen equation. D acting on e to the I omega t equals I omega e to the I omega t. Like this. Okay, so if you now consider e to the I omega t as as a point on the complex plane, right? This is Euler's formula. E to the I omega t is a point on the unit circle. We explained that in our complex variable videos and live streams. So what does this do? It's just a rotation. Complex multiplication is rotation times I omega means rotation by 90 degrees and scale by omega. So yeah, see, this means that the AC theory in complex numbers is just a convenient choice of basis representation. I omega t is eigenfunction. Are you using a mouse? Yes, I'm using a mouse. This is how I usually write stuff on live streams. Yeah, I don't have a pen. So basically, if we come to the original definition, what do we have? So let's think about, let's think about V as, typically you think of V as the cause, right? The voltage is the cause and the outcome, the result is the current. Think of V as the cause and I as the outcome. So for capacitor, differentiation is acting on V. It gives you the current. So therefore, for capacitor, what happens? If V acting, see, you get this is, this is the e to the I omega t. Differentiation, after differentiation, you get I omega e to the I omega t, right? So this tells you that capacitor has a the phase of the capacitor is half pi ahead. And now the inductor, well, for the inductor, you see, you can write it as this way. So I is D inverse 1 over L D inverse. 1 over L doesn't matter, it's just a scalar. D inverse of V. What about D inverse? Well, D inverse is just, it lags by half pi. So if this is V, okay, if this is V, then for resistor, it's the same phase. Resistor is always in sync with the voltage. Capacitor is half pi phase ahead, right? And the inductor is half pi lagging behind. So that's the Heaviside theory of complex number, Heaviside theory of alternating current. Because in alternating current, you only deal with sine and cosine anyway. So you get a finite dimensional vector space. You can represent differentiation with respect to that vector space using eigenfunctions. And the eigenvalue is just I omega. So it's just either rotate by half pi, is rotate by half pi, counterclockwise or clockwise. So therefore, you get the expression for the what we call impedance, right? Yeah, impedance comes from this way. Right? So V is you can V for resistor R times I. For capacitance is ZC times I. For inductor ZL times I. Okay. Typically, yeah, this is you can get the formulas for ZL is I omega times L. Okay, and ZC. Let me think. DC using this formula. DC should be, because I don't remember all these formulas, but DC, yeah, DC is 1 over I omega C. It's just eigenvalue decomposition. So there is a website containing a complete topology course with problem sets from University of Toronto. Can anyone provide a link of it? How did you write basis for? Yeah. So I was saying like the basis is now, because earlier we said the eigenfunctions for the differential operator in general is exponential. So all you need to do is to determine the eigenvalue. Then minus s, if the eigenvalue minus s is determined, then the exponential function is determined, right? So here, you see we have the original basis is sine and cosine. The original basis is sine and cosine, but now it turns out that the eigenbasis is e to the plus or minus I omega t because of the lambda. Okay, the original basis is sine and cosine. That's the natural choice, but it's not the most convenient choice, because using the eigenbasis turns differential operator into scalar multiplication. It's just that the scalar is complex. So doing electricity, doing AC with respect to the eigenbasis is much more convenient, and hence you get the phasor method. It's a linear algebra problem. It turns differentiation into algebra. Right? This is a recurring theme we've done many times, right? Convolution, difficult calculus problem turns into multiplication. Differentiation, difficult calculus problem turn into multiplication. You say, how do you write basis for those two? Oh, okay, how do you write, you mean these two? Yeah, so subhac, so you mean these two lines, right? So this is just calculus. The basis is cosine omega t and sine omega t. This is 0 times cosine minus omega times sine. So this is 0 omega, 0 minus omega. Okay, so let me write that. Okay, so this is the first coefficient, 0 times cosine of omega t minus omega sine omega t. You just extract the coefficients and put them as a column vector. That's the coordinate vector. Same thing here. Omega times cosine omega t plus 0 sine of omega t. Extract the coefficients, put them in a vector. And then put these two column vectors together into a matrix. and then do the diagonalization. Are we clear? Okay, so that's another example of representing functions with respect to a convenient basis. Instead of working with sine cosine, we work with exponential, complex exponential, because of eigenvalue, eigenvector. Okay, so I want to get to Fourier transform. How do you not confuse omega with resistance is big R. Omega has nothing to do with R, right? Omega is just is a constant. But omega is determined by how fast your generator turns. Physically, they're totally irrelevant. Okay. Anyway, so in the final part of this stream, I want to introduce discrete Fourier transform because I have no time to introduce Fourier series and continuous Fourier transform, but it still get the idea across. Discrete Fourier transform and the OG discrete Fourier transform and not fast Fourier transform, because fast Fourier transform, after all, is just a computational algorithm, right? The algorithm that speed up calculation, right? It has nothing to do with the fundamental idea we discuss here, namely eigen composition. Right? Integral transformation fundamentally is a linear algebra idea. And analysis would just help with the complicated math, the infinite dimensional spaces, that kind of stuff. But the fundamental idea is linear algebra. Discrete Fourier transform. No, you're not taking too much of my time, bro. I said many times this is a seminar, okay? It's not a lecture. I have a rough idea what am I talking about, but I have no lecture plan. Okay, I have to finish topic X. No, you're not taking. My point here is to give my own understanding and answer questions, and also perhaps sometimes correct my own mistakes. And it actually happens a lot of time. There are viewers who pointed out my mistakes. This is a mutual thing. The transform, discrete Fourier transform. Does this have anything to do with transform? You mean transformers from deep learning, like language model? I don't think so. It's a different concept. I suppose you're talking about the transformers from deep learning, or you're talking about transformers from electrical engineering, like the physical device of a transformer that changes the voltage. This is a mathematical construct. It has nothing to do with hang on. Yeah, it has nothing to do with electrical engineering per se. Although we gave an example, this was purely discussed mathematically. Right? It's just this was just you can abstract it to how linear operator D, differential operator, act on the space spanned by cosine and sine. Okay, and not much else, at least that's as far as I understand. Okay. Anyway, so let's talk about discrete Fourier transform. Now let's once again go back to the discrete setting, right? Consider a purely linear algebraic problem. Okay. So let's consider a vector or finite sequence, because now we've seen the usefulness of complex numbers. So let's consider a vector in a complex vector space Cn. Consider S is an operator on Cn. And what S does is very simple. it does a cyclic shift. Oh, okay. So no, it doesn't. I don't think it has to do with the transformer, the actual physical transformer. Okay. The actual physical transformer is based on the Faraday's law or Lenz's law, or actually my electrical stuff is already kind of forgotten. Transformer in alternating current. You're talking about this transformer. It's a physical device, and the physics is Faraday's law of induction, as I sort of remembered. Okay, yeah. So basically, you can amplify the voltage by changing the ratio of how many times you wrap around the coil. I don't know how did I even call. Okay, so basically, I forgot my electrical stuff a long time ago. So n is the number of turns. Yes. So the fundamental identity is this one. The voltage is proportional to the number of terms. It has nothing to do with Fourier transform. Okay, it's just the name. Okay. This is based on Faraday's law. Okay, so we're not getting there. Okay, so finally, I mean, in this last section, I wanted to talk about discrete Fourier transform. So this is a purely mathematical operation. So S of a vector u1 all the way to un is defined as follows. So you want to shift, okay? You want to shift the coordinates as such. So u2 occupies, the original u2 now occupies u1's position. Okay? And then everything else that follows. So everything after u1 gets moved one position forward. So it reads u2, u3 all the way to un, right? But this is m-1 coordinates. What about the last one? Well, the last one, u1 gets shifted to the end. Right? This is called the cyclic shift mapping. This is called the cyclic shift mapping, defined by this, from Cn to Cn. So S has an obvious property. S preserves the Euclidean norm. That is to say, this operator S is first of all, is linear, obviously. Oh, my cat. So S is a linear operator, obviously, and it's also an isometry. Isometry in the sense that it preserves length. Or actually, it's called unitary. In isometry, it preserves distance. Here, it preserves norm. It's called the unitary operator. It preserves length. It's linear and unitary. S is unitary means it preserves length. Means the Euclidean norm of S of u equals the Euclidean norm of u, where Euclidean norm of u, the square Euclidean norm of u is defined as the sum of k from 1 to n uk modulus squared. Remember, each coordinate is now complex number. So this is complex modulus, okay, not just a complex number squared. Okay, it is a fundamental fact from linear algebra that a unitary operator is orthogonally diagonalizable. Okay, actually, if this fact is a little bit unfamiliar, let's go to the linear algebra module. It's typically introduced in linear algebra 2, complex vector spaces. So unitary operators are direct generalization of orthogonal operators. Orthogonal operators basically preserve Euclidean lengths as well, but in Rn, not Cn. Okay. Here in this lesson, complex diagonalization, a fundamental fact is unitary operators are are unitarily diagonalizable. Do we have that here? Anyway, because I don't have a lot of time, I will just write down the theorem. You can I think you can I'm pretty sure you can find it here. Okay, so this is S is unitary. It preserves, i.e., S preserves Euclidean length. And the file is getting a bit too long, so things are very laggy right now. So a fundamental result in linear algebra is as follows. Okay, unitary mappings have a complete set of orthogonal eigenvectors. Unitary operators. It's guaranteed simply because it preserves length. Have a set, a complete set. God damn it. Sets of orthogonal eigenvalues, orthogonal eigenvectors. Let's just call them EJ, orthogonal eigenvectors, and eigenvalues lambda j such that the complex absolute value, or the modulus of lambda j, equals 1. This is a fundamental result, okay, from linear algebra. Okay, so why is this important? Why does this has anything to do with discrete Fourier transform? Well, you probably see where this is going. We're going to diagonalize S. So let's calculate the eigenvalues. Okay, so here, let's calculate the eigenvalue. Value eigenvectors of S. So the equation says SE equals lambda E, right? E is an eigenvector. Eigenvalue is lambda. Right. So, well, let's write E equals U1 all the way to UN. These are the components of E. So what is SE? Well, SE by the definition is U2, U3, all the way to UN, and U1. And this equals lambda U1, lambda U2, all the way to lambda UN. So you get a bunch of equations for the component. So U2 is lambda U1. U3 is lambda U2. You see a pattern here? And all the way to un equals lambda un minus 1, and lastly u1 is lambda un, just setting all the components to be the same. Okay, so, well, remember, when you calculate eigenvalue and eigenvectors, you won't get a unique solution. You won't get a unique solution because if you multiply both sides by a constant, the equation still holds. Right? So you will never get a unique solution when it comes to calculating eigenvalues. So for that reason, we can choose one corner to be free, to be whatever value which we find convenient. And for that, we can pick u1 just to be lambda. Okay, and the advantage of doing so will become transparent later. Okay, so the idea is you can always pick one corner to be whatever you want because of the fact that the equation is homogeneous. You can multiply a constant on both sides, the equation still holds. So picking u1 to be lambda, you get u2 is just lambda squared, and u3 is lambda, what is lambda cubed. So all the way to un is lambda to the n. But now here comes the last equation. Here comes the last equation, and which says lambda equals lambda times lambda to the n. This means lambda to the n must be 1. Lambda to the n must be 1. So what does that mean? This is a complex equation. Remember, lambda is complex. So that means lambda is the nth root of unity. The eigenvalue lambda is the nth root of unity. So to calculate the nth root of unity, this is a basic problem in complex numbers. We haven't done so in our complex analysis series. I think actually we did that. We did that last week when it comes to calculating nth root of complex numbers. But basically, here's how it works. Okay, here's how it works. So we can first write 1. So lambda to the n, this is equal 1, right? So 1 on the complex plane can be represented as follows. So this is the unit circle on the complex plane. This is e to the I of 0. E to the I of 0. So in general, if this is t, this angle is t, then this complex number is e to the it. When t is 0, this is exactly 1 on the real axis. But of course, this is not the only representation, right? Because you can simply add the angle by integer multiple of 2 pi and get the same point. So this is just e to the I 2 pi n. N is an integer. Okay? Oh, actually we can use n. N is already occupied. So let's use k. This is k. So now you can write lambda as e to the I 2 pi k over n. E to the 2 pi k over n, all right? And the thing is, the k here, because as I said, k is an integer, right? Here, the k can take integer value, but eventually, if you run k from 0, 1, 2, and so on, eventually it will repeat itself. Okay, let's draw the picture to see what's going on. For example, if n is, say, 2. If n is 2, let's look at the nth root of unity of n equals 2. Okay, so we all know from high school if you take the square root of 1, you get plus or minus 1. And that's exactly what's happened here. So when n equals 2, you get two roots, which is e to the I of 0 and e to the I of pi. These are 1 and minus 1. The nth root of unity when n equals 2. So when n equals 3, you get 3 points on the unit circle. So notice when n equals 3, this 2 pi over 3 is, well, pi over 3. You start from 0 because 1 is always a root. E to the I of 0 is always a root. And when k equals 1, it goes here. So this is e to the I 2 pi over 3. And when k equals 2, you rotate by another 2 pi over 3, so that's e to the I 4 pi over 3. Right? So the idea is all those cubic roots lie on a regular triangle. Right? So this is a regular polygon. N equals 3. This is a triangle. And when n equals 4, I'll just draw the final example. In general, the nth root of unity lies on a regular n polygon on the unit circle. Okay, so when n equals 4, you get e to the I of 0 here, and then so k equals 1, you get e to the I pi over 2, and e to the I pi, and finally e to the 3 pi over 2. So you don't need any to let k to be any integer. That's my point. So k can just run from 0, 1 all the way to n minus 1. This will give you all the roots. These are all the possibilities here. Okay, so this is the nth root of unity. Okay, and what we can do is, you have what we managed to calculate. This is eigenvalues. Okay, these are the eigenvalues, and notice this is consistent with the big theorem. The eigenvalues all have length equals 1 because they all lie on the unit circle. Okay, this is consistent. We actually have the expression here. They all have eigenvalues that's on the unit circle. Okay, so what about the corresponding E? These are eigenvalues, so the eigenvectors is now also written. This is just a standard problem in linear algebra, although with complex numbers. Okay, so this might be a little bit less familiar, but the idea is the same. We're still doing eigenvalue decomposition. So Ej is what? Ej, let's just call them lambda j. Okay, lambda j is I 2 pi j over n, and Ej is lambda j. This is u1, right? U2 is lambda j squared, lambda j cubed, all the way to lambda j to the n. This is our j's eigenvector. So now what do? You can do eigenexpansion. You have the eigenvector j from 1 to all the way to n. Let's summarize our result. Okay, this is the eigenvalues, and this is the eigenvector. With eigenvalue and eigenvector, you can do eigenexpansion. Okay, so let arbitrary u be in Cn. Let arbitrary u be in Cn, so you have u written as a linear combination, j from 1 to n, aj, ej. But how do you do this expansion? Here is where orthogonality comes into play. If you have orthogonal vectors, coefficients are very straightforwardly obtained. So let's write u equals u1 all the way to uk again, un again. Let's say if I want uk, what can I do? These are guaranteed to be orthogonal. Ej inner product with E, I can use I, but let's say Ej Ek inner product is 0. You can always do that. You can verify that. So the big theorem, I mean, there's no need to verify, but you can. The big theorem says the eigenvectors are all orthogonal. Orthogonal eigenvectors makes expansion extremely easy. Just like you do expansion of vectors in x, y, z coordinates. Right. Orthogonal bases, they make orthogonal expansion, they make the expansion looks very easy. Okay, so yeah, due to orthogonality, I will continue this probably next time. I'm getting too tired here. Basically, what happens is Aj, the expansion coefficient, is the inner product of u with Ej. You just, to take the, because of orthogonality, okay, let me just, perhaps not familiar to everyone. Oops, that's my video game. So you get E1, say E1, E2, E3, as an example, okay. So here, because of an arbitrary vector, say u is C1, A1, E1 plus A2, E2. The expansion is easy purely due to orthogonality. So that's why Fourier transform is very popular, because you have this orthogonality baked in. Okay, A3, E3. So, for example, if I want A1, I can just take the inner product U with E1. So this way, you get A1, E1 with E1. And because E1 is orthogonal to E2, E1 is orthogonal to E3, the last two terms cancel, and A1 is just U E1 with E1 over E1 E1. So Aj is Ej, U taking inner product over Ej, Ej. Okay? And then you just use the product for the dot product formula. Guys, I'm a little bit tired. So here the expansion coefficient is 1 over n, because this turns out to be 1 over n. Okay, this turns out to be, the denominator turns out to be 1 over n, and then you sum, this is the dot product formula you get from here earlier. That's the expression for the coefficient, lambda j, and here you had, my goodness, how can I forgot the e? E. Okay, there's an E there, my God. As you can tell, I'm probably too tired. J from 1 to, okay, let's write K. Okay, K from 1 to N, UK, and then E to the minus, okay, E to the minus 2 pi I over N, and then JK. Yeah, so yeah, we'll continue this next time. Okay, this is the coefficient, and from the coefficients you can of course reconstruct U. So this is the discrete Fourier transform. No worries. And then you also have the discrete inverse Fourier transform. Discrete inverse Fourier transform is basically this thing. Okay, it's basically the same. I just need to write it in component form. Okay. Anyways, sorry for this. And I really need to go because it's already 4 hours and a half. Okay, so I can't do this any longer. Okay, we'll continue this time. Transform is a big topic. I have to talk about continuous Fourier transform. No worries. Okay, so the distinguishing feature of Fourier transform from the earlier transform is that it has an orthonormal basis. It has an orthogonal basis. It doesn't have to be orthonormal, but orthogonal basis. Earlier, the bases don't have to be orthogonal. Okay, and orthogonal basis makes computing expansion coefficients super easy and also numerically stable. Let's not forget that. Numerically, Fourier transform is much well behaved compared to Laplace transform. All right, thank you guys for watching, and I'll see you next time.